The idea that we only use 10% of our brains is a myth. This claim has been around for over a century. It's often repeated in books, movies, and motivational talks. But it's not true. Brain scans show that activity happens across the entire brain, even when we're not doing much. Scientists have tested this myth many times. Every time the evidence shows that we use all parts of the brain. Your brain is always active. If you are only using 10%, damage to the other 90% shouldn't matter. But that's not the case. A stroke that affects just a small part of the brain can cause serious problems. People may lose the ability to speak, walk, or understand language. This shows how important each part of the brain is. Let's look at how the brain works. The brain has different regions. Each region does something important. The occipital lobe handles vision. The temporal lobe helps with hearing and memory. The frontal lobe controls thinking and decision-making. The parietal lobe helps you feel touch and understand space. The cerebellum helps you move smoothly. The brainstem keeps you alive by controlling your heart rate and breathing. No part of the brain sits idle. Even when you're resting, certain areas stay active. These include regions involved in daydreaming, memory, and self-reflection. This network is called the default mode network. It lights up when you're not focused on the outside world. Brain scans like fMRI and PET scans show how the brain uses energy. These scans show that almost all parts of the brain get used during a normal day. For example, just listening to someone speak can activate several regions. Your brain decodes the sounds, figures out the meaning, and stores it for later. All of this happens in real time, and it involves far more than 10% of the brain. Consider a task like making a sandwich. You might think it's simple, but it takes many brain regions working together. First, you use your eyes to see the bread and the knife. Then your brain guides your hand to pick up the knife. As you spread the peanut butter, your brain keeps track of the force you use so you don't tear the bread. You recall where you put the jelly, decide how much to use, and remember how your friend likes their sandwich. These small actions involve memory, planning, motor control, and vision. All of them rely on different parts of the brain. That's far more than 10%. Brain damage studies also disprove the myth. When people suffer injury to even a small area of the brain, the effects can be dramatic. A lesion in Broca's area can make it hard for someone to form words. Damage to the hippocampus can wipe out short-term memory. These effects show that most of the brain is doing important work. There's no extra space just sitting unused. The 10% myth might have started with a misunderstanding. In the late 1800s, psychologists like William James wrote that we use only a small part of our mental resources. He meant that we don't reach our full potential. He wasn't talking about brain activity. Over time, this idea may have been misquoted. People may have started saying that we only use 10% of our brains. The media picked up the idea. It spread fast because it sounds exciting. It gives people hope that they can unlock hidden abilities. But it's not based on science. Hollywood has played a big role in keeping the myth alive. In movies, characters unlock their unused brain power and gain superhuman skills. This makes for fun stories, but it misleads people. The truth is, human brains already do amazing things. They control our thoughts, actions, emotions, and memories. They learn languages, solve problems, and adapt to change. These aren't signs of a brain running at 10%. They're signs of a brain working at full capacity. People sometimes ask, if we use all of our brain, why can't we remember everything? The answer lies in how memory works. Memory is selective. The brain filters out what's not important. That's not waste, it's efficiency. A brain that remembered every sound, sight, and smell would get overwhelmed. Forgetting helps us focus on what matters. It's a feature, not a flaw. There's also the question of brain reserve. Some people live normal lives even with brain damage. Does that mean they weren't using that part of the brain? Not quite. The brain can rewire itself, especially early in life. This is called neuroplasticity. If one area gets damaged, other areas can sometimes take over. But this comes at a cost. Recovery can be slow, and not all functions can be recovered. Again, this shows how vital every part of the brain is. Brains are energy hungry. They use about 20% of the body's energy, even though they make up just 2% of body weight. Evolution tends to weed out waste. If 90% of the brain were useless, nature would likely have trimmed it down. The fact that it's still here and still so demanding tells us it's all doing something important. Even during sleep, the brain is busy. It organizes memories, clears out waste, and recharges. Scientists have found that sleep helps us learn and remember. If only 10% of the brain mattered, why would the whole thing stay active at night? Sleep studies show that many brain regions light up in patterns as we go through different sleep stages. This tells us that rest is an active process, not downtime. Brain scans of people in comas show reduced activity, but not none. Doctors can sometimes predict recovery chances based on how much of the brain is still active. This wouldn't be possible if 90% of the brain didn't matter. The loss of even small areas can make recovery less likely. Teachers and self-help speakers sometimes use the 10% myth to motivate people. They want to say, "You can do more." That message isn't bad on its own, but the science behind it doesn't hold up. People can grow, learn, and improve, but they do it with a brain that's already firing on all cylinders. No part of the brain is just sitting there, waiting to be activated. What people often mean when they talk about untapped potential is skill, not brain tissue. They mean that you can improve your focus, discipline, or creativity. And that's true. But it doesn't mean large parts of your brain are sleeping. It means you can make better use of your time and energy. Understanding how the brain works helps us make better choices. It clears up myths. It sets realistic expectations. And it shows just how complex and capable the human brain really is. The idea that people are either left-brained or right-brained has become a common way to describe how people think. According to this belief, logical people use the left side of their brain more, while creative people rely on the right side. This claim is easy to understand, and it sounds scientific, but it isn't accurate. Brain research has shown that both sides of the brain work together for most tasks. You can't separate logic from creativity, and you can't assign one half of the brain to each. This myth likely started with early studies in neuroscience. In the 1960s, researchers looked at patients who had their corpus callosum cut. The corpus callosum is the bundle of nerve fibers that connects the left and right sides of the brain. Surgeons sometimes cut it to treat severe epilepsy. These split-brain patients gave scientists a rare chance to study each side of the brain in isolation. What the studies found was that the left side of the brain played a bigger role in language, and the right side handled more spatial tasks. These findings were real and important, but people took them too far. Soon, the science got simplified for the public. Writers and speakers claimed that if the left hemisphere did language, it must also do logic, numbers, and facts. If the right hemisphere did spatial tasks, it must be in charge of creativity, emotions, and art. This leap was not backed by data. It turned complex brain functions into a simple story about personality. That story stuck, but it's not how the brain works. The brain is lateralized to a degree. Some functions do show stronger activity in one hemisphere. For example, Broca's area, a key region for producing speech, is usually in the left hemisphere. The right hemisphere plays a larger role in recognizing faces. But this does not mean that only one side of the brain handles each task. It also doesn't mean that a person favors one hemisphere over the other in everyday life. Most activities require both sides of the brain. They work as a team, passing information back and forth through the corpus callosum. Think about reading a sentence. The left hemisphere helps with decoding words and grammar. The right side helps you understand tone, emotion, and context. Both sides must coordinate to grasp the full meaning. Or take music. The right hemisphere does play a strong role in pitch and melody, but rhythm and timing often involve the left side. Musicians use both hemispheres when they play or compose music. Even logic and creativity are not easy to separate. Solving a math problem may seem logical, but it often requires creative thinking to find the best approach. Writing a poem may seem creative, but you still need logical structure and syntax. In real life, logical and creative thinking go hand in hand. The brain does not sort them into separate bins. Studies using brain imaging tools like fMRI show that people don't favor one side of their brain. When researchers looked at activity in over 1,000 participants, they found no evidence that some people rely more on the left or right hemisphere. Instead, they saw patterns of activity that spanned both sides. Whether solving puzzles or drawing pictures, the brain showed integrated function. People who say they are right-brained often mean they enjoy art or music. People who say they are left-brained may enjoy math or science. These preferences are real, but they don't come from one side of the brain being more active than the other. They come from a mix of personality, education, interest, and experience. Your brain does not lock you into one way of thinking. Let's consider a common example: writing a story. You might think this is a job for the right brain. It involves imagination and emotion. But to write well, you also need structure, grammar, and planning. You need to remember what you wrote earlier and keep track of where the story is going. These skills involve working memory, attention, and language, all of which rely on both hemispheres. Again, both sides contribute. Another example is driving a car. It involves spatial skills, which are often linked to the right hemisphere, but it also involves reading signs, listening to directions, and following rules, all of which involve the left hemisphere. Most tasks in daily life work like this. They're not controlled by one side of the brain. They require teamwork across the brain. The myth of left-brained and right-brained people can even be harmful. It may cause someone to believe they're not a creative type or not good at math because they think their brain just isn't wired for it. But the truth is, people can learn and improve in many areas. The brain is adaptable. It changes with use, a trait known as neuroplasticity. With practice, people can develop skills that seem outside their comfort zone. There are also differences between people, but they don't map neatly onto brain halves. Some people may have stronger verbal skills or visual skills. Some may think in pictures, others in words. But this variety doesn't mean one half of their brain is doing all the work. It just means that different brain networks have developed in different ways. Neuropsychologists sometimes test for lateralized function. For instance, during brain surgery, they may use the WADA test to see which side of the brain handles language. This test helps doctors avoid damaging critical areas, but these tests are about function, not personality. They don't tell us if someone is creative or logical. They just show where certain processes happen. Children are often told they are left-brained learners or right-brained learners, but this idea has no strong backing in education science. Effective teaching considers the whole child, their interests, strengths, and learning history. It doesn't split learners by brain side. Good teaching uses multiple approaches. It might involve visual aids, hands-on practice, and spoken instruction, all of which use both sides of the brain. Even in brain injuries, people don't become purely logical or creative based on which side was damaged. Damage to one side may cause certain language or spatial problems, but personality, thinking style, and interests are more complex. They arise from many brain regions working together. There is no shortcut to pinning these traits on half a brain. The brain is a network. It has specialized areas, but they're all connected. Each hemisphere contains versions of the frontal, temporal, parietal, and occipital lobes. These areas link through circuits that process attention, memory, emotion, and reasoning. Most meaningful tasks light up several of these areas. Imaging studies show this again and again. People are not left-brained or right-brained. they are whole-brained. They use different brain regions in flexible ways, depending on the task. Logic and creativity are not at odds. They are partners, and the brain does not pick sides. It works as a whole system, built for complexity, not for easy labels. Many people believe that brain damage is always permanent. This belief is common because the brain is complex, and injury to it can lead to serious problems. But the idea that nothing can improve after damage is not correct. The brain has a special ability called neuroplasticity. This means it can change, adapt, and even rebuild certain functions over time. Recovery is not always complete, and progress can be slow, but improvement is often possible, especially with therapy, training, and support. Neuroplasticity refers to the brain's ability to form new connections between neurons. When part of the brain is damaged, other areas can sometimes take over. These changes don't happen overnight, and they depend on many factors, such as the person's age, the type of injury, and how soon therapy starts. Still, recovery happens more often than most people think. Take stroke, for example. A stroke can damage areas of the brain responsible for movement, speech, or memory. In the early days after a stroke, a person may be unable to walk, speak, or use their hand. But with therapy, many people recover these abilities. The damaged neurons may not come back, but other neurons can learn to do similar work. In some cases, parts of the opposite hemisphere may take over the job of the damaged area. This is a direct result of neuroplasticity at work. Consider a person who loses the ability to speak due to a stroke affecting Broca's area in the left hemisphere. In the weeks and months that follow, the brain can reorganize itself. Therapists may guide the patient through speech exercises that strengthen language networks. Other parts of the brain can begin to support speech production. With time, the person might regain basic language skills or even full speech. This recovery would not be possible if all brain damage were permanent. In younger people, the brain's ability to adapt is even greater. Children who suffer early brain injuries can sometimes recover in ways that surprise even doctors. For example, a child who loses part of a hemisphere can still grow up to speak, read, and move well. The remaining tissue takes over functions lost from the damaged side. Their brains rewire more easily because young brains have more plasticity. Even in adults, the brain can change. People who suffer traumatic brain injuries from accidents or falls may have memory loss, confusion, or trouble with attention. Over time, with targeted therapy and support, they often make gains. Rehabilitation might include physical therapy, occupational therapy, or cognitive training. These treatments don't heal the brain directly. Instead, they help the brain create new patterns and workarounds. Repetition plays a big role in recovery. When a person repeats a task again and again, it helps strengthen the brain circuits involved in that task. It's like learning to play a musical instrument. The more you practice, the stronger the connections in your brain become. In brain injury rehab, a similar process happens. If a person practices moving their hand every day, even if it's hard at first, the brain adapts. Over time, the movement becomes easier. The brain builds new connections to support that action. Technology can also support brain recovery. Tools like functional MRI allow doctors and researchers to see how the brain changes over time. They can watch as new areas become active when a person tries to speak, move, or solve a problem. This helps confirm that neuroplasticity is real, and it shows how recovery happens at the neural level. Virtual reality, robotic tools, and brain-computer interfaces are also part of modern therapy. These tools give patients ways to interact with their environment and get real-time feedback. For example, a person learning to use their arm again after a stroke might practice using a robotic exoskeleton. The repeated movement helps rebuild brain circuits involved in motor control. Psychological recovery is also possible. People with brain injuries often struggle with mood, behavior, or memory. Therapy can help them learn coping skills, set routines, and build strategies to support their thinking. This is another kind of adaptation. It may not restore what was lost, but it helps people function well with the brain they have. Not all brain damage can be fully repaired. In some cases, neurons are lost and cannot regrow. Some injuries are so severe that full function never returns. But even then, people often adapt. They find new ways to live, work, and relate to others. Sometimes family members or caregivers help with tasks. Other times, people learn to use tools like memory aids, speech-to-text apps, or mobility devices. These changes show that recovery isn't just about the brain fixing itself. It's also about how people adjust and learn new ways to manage. One example is a man who suffers a brain injury in a car crash. At first, he can't remember names or follow conversations, but with support, he learns to take notes, use reminders, and plan his day in smaller steps. Over time, he rebuilds some memory skills and learns to rely on tools for the rest. His brain changes, and so do his habits. He may not be the same as before, but he improves and adapts. Some people assume that once a doctor says, "You have brain damage," nothing else can be done. But this isn't true. The diagnosis is the start of a process. Rehabilitation is often long and requires effort, but it can lead to major gains. Doctors, therapists, family, and the person themselves all play a role. The brain's flexibility makes it possible. Brain damage also varies in how it affects people. One person with a concussion might recover fully in weeks. Another with a similar injury might take months. A person with a tumor removed from their brain might lose vision on one side, but still function well in daily life. A soldier who suffers a blast injury may take a year to rebuild attention and memory. These stories show that outcomes are different for everyone, and that recovery depends on many things, not just the damage itself. Even people with long-term brain damage can make progress years after the injury. It was once thought that if recovery didn't happen in the first few months, it never would. But new research shows that gains can happen later, especially if therapy continues. The brain keeps learning. It keeps adapting. There is no strict deadline for recovery. Neuroplasticity is not magic. It has limits, but it's powerful. It changes how we understand the brain. It gives people hope based on evidence, not wishful thinking. Brain damage is serious, and it can change lives, but it does not always mean the end of growth. The brain can change its structure and function. With time, work, and the right support, recovery is possible. Many people believe that brain cells can't regenerate. The phrase, "you can't grow new brain cells," has been repeated for years, even by teachers and doctors. It's easy to think that once brain cells die, they're gone forever. This belief made sense for a long time because scientists didn't have the tools to see what was really happening inside the brain. But research over the last few decades has shown something different. The adult brain can, in fact, produce new neurons. This process is called neurogenesis. Neurogenesis happens mainly in one part of the brain, the hippocampus. This area is involved in memory, learning, and mood regulation. In both animals and humans, studies have found that new neurons form in the hippocampus throughout life. This doesn't mean the brain replaces every lost cell or that all parts of the brain regenerate equally. But it does mean the adult brain has some capacity to grow new neurons and rewire itself in response to experience. Scientists first observed neurogenesis in birds. In the 1960s and 1970s, researchers found that some bird species grew new brain cells during certain seasons, especially when learning new songs. This raised the question, could mammals do the same? For a long time, most experts said no. but in the 1990s, research using advanced tracing techniques showed that new neurons do appear in the hippocampus of adult rats. These findings were later confirmed in humans. One key study examined the brains of cancer patients who had received a compound called BRDU. This compound helps mark dividing cells. After these patients died, researchers looked at their brain tissue and found signs of new neuron growth in the hippocampus. This was strong evidence that adult human brains could form new neurons. The rate of neurogenesis slows with age. Children and young adults produce new brain cells more quickly. As people get older, the process slows down, but it does not stop. Even in elderly people, there is some level of new neuron growth. Lifestyle factors can influence this process. Exercise, mental stimulation, and social engagement all appear to support neurogenesis. In contrast, chronic stress, poor sleep, and lack of stimulation can reduce it. Exercise is one of the most well-studied ways to support brain cell growth. In animal studies, rats that run on wheels show more new neuron formation in the hippocampus than rats that don't. Similar effects appear in people. Aerobic activity like walking or cycling has been linked to improved memory and cognitive performance. Researchers believe this is partly due to increased neurogenesis. Exercise also boosts blood flow to the brain and raises levels of brain-derived neurotrophic factor, or BDNF, a protein that supports neuron survival and growth. Mental stimulation plays a role as well. Learning a new skill, reading, or solving puzzles can help keep brain networks active. These activities may not directly cause new neurons to form, but they create an environment where neurogenesis is more likely to occur. They also help new neurons integrate into existing networks, which is key to making them useful. Sleep supports neurogenesis too. During sleep, the brain clears out waste and consolidates memories. Poor sleep can interfere with the brain's ability to maintain and grow neurons. Studies have found that animals deprived of sleep show lower levels of neurogenesis in the hippocampus. Stress has the opposite effect. When a person faces long-term stress, the brain releases more cortisol. High cortisol levels can shrink the hippocampus and reduce the rate of neurogenesis. This may explain why chronic stress is linked to memory problems and mood disorders. Reducing stress through mindfulness, therapy, or lifestyle changes can help protect the brain's ability to form new neurons. Even though neurogenesis happens mostly in the hippocampus, the rest of the brain is not fixed in place. Other forms of plasticity also help the brain adapt. Existing neurons can form new connections. Synapses can strengthen or weaken over time. Brain regions can shift their roles in response to injury or experience. These changes don't involve new neurons, but they show that the brain is more flexible than once believed. Some brain injuries trigger changes that look like regeneration. After a mild injury, the brain may increase production of certain growth factors. These help repair tissue and sometimes support the formation of new cells. The brain's ability to respond this way is limited, especially in severe injuries. But it shows that the adult brain has some tools for self-repair. It's important not to overstate what neurogenesis can do. It does not mean the brain can fully heal from any damage. It does not mean lost memories can come back, or that brain diseases can be reversed. But it does show that the brain is not static. It keeps changing throughout life, and new neurons are part of that change. There is still debate among scientists about how much neurogenesis happens in older adults. Some studies have found strong evidence of new neuron growth, while others have reported lower levels or no clear signs. These differences may be due to research methods, the health of the people studied, or how samples were collected. But most researchers agree that some level of neurogenesis continues throughout life, especially in healthy brains. One practical example of neurogenesis at work is in patients with depression. The hippocampus is often smaller in people with long-term depression. Antidepressants have been found to increase levels of BDNF and promote new neuron growth. In some cases, this may help restore function in the hippocampus. This does not mean neurogenesis cures depression, but it may play a role in recovery. Another example is learning a new language. This kind of learning challenges the brain in multiple ways. It involves memory, attention, and auditory processing. Studies suggest that language learning, especially in immersive environments, can lead to structural changes in the hippocampus. These changes may include new neuron formation as well as growth of connections between existing cells. Even social interaction matters. Loneliness and isolation can reduce brain health and lower rates of neurogenesis. Spending time with others, having conversations, and building relationships all help keep the brain active. This kind of engagement supports not only mood, but also cognitive function. The idea that brain cells can't regenerate was once seen as fact. It fit with what scientists knew at the time. But as tools improved and more research was done, that view changed. Now we know that neurogenesis happens in adults, especially in the hippocampus. This growth is limited and influenced by many factors, but it is real. The brain is capable of more change than once believed. It does not stop growing the day we become adults. With the right conditions, movement, learning, rest, and connection, it can continue to adapt and form new cells. Many people believe that bigger brains mean smarter people. It seems like a simple idea. More brain tissue must mean more thinking power. But brain research tells a different story. While there is a small link between brain size and intelligence, it's not strong or direct. Other factors like brain structure, connections, and how efficiently the brain works play a much larger role. The average adult human brain weighs about 3 pounds. Some people have brains that are a bit bigger or smaller than this. Men, on average, have larger brains than women, but this doesn't mean men are smarter. When scientists study intelligence and brain size, they find only a weak correlation. That means brain size explains only a small part of the differences in how people perform on tests or solve problems. In many cases, people with smaller brains perform just as well or better than those with larger ones. One reason brain size doesn't tell the full story is that the brain has many parts and not all of them relate to thinking. The brain includes regions that handle basic life functions like breathing, balance, and heartbeat. These areas don't directly affect problem solving or memory. So a bigger brain might mean a larger brainstem or cerebellum, not necessarily more capacity for reasoning or learning. What matters more than size is how the brain is built and how it functions. The brain's outer layer, called the cerebral cortex, plays a big role in thinking, decision-making, and language. Within the cortex, the structure and density of neural connections are more important than its volume. For example, the number of folds in the cortex, called gyrification, can affect how much surface area fits in the skull. More surface area often means more space for complex thought, even in a smaller brain. Another important factor is how different brain regions communicate. Intelligence depends on the ability to combine information from many sources. This involves long-range connections between different areas of the brain. These pathways are made up of white matter. Studies have shown that the quality of these connections, how well information moves between regions, matters more than how big the brain is. Efficiency is also key. Some people use their brains more efficiently than others. This means they solve problems with less effort or use fewer brain regions to do the same task. In brain imaging studies, smarter individuals often show less activity in some areas during simple tasks. Their brains don't need to work as hard. This kind of efficiency suggests that it's not about having more brain, but using what you have in a better way. Consider Albert Einstein. His brain was not especially large. In fact, it was slightly smaller than average. But when scientists studied the structure of his brain, they found that parts of his parietal lobe, which are involved in spatial reasoning, were different. He also had unusual patterns of folding in the cortex. These features may have supported his ability to think in ways that others didn't. You can also look at animals for more clues. Elephants and whales have much larger brains than humans, but they don't outperform humans on cognitive tasks. What sets humans apart is not size, but complexity. The human brain has a large and highly developed prefrontal cortex, which supports planning, language, and abstract thinking. The way neurons are packed and organized in this region gives humans an edge. Brain-to-body ratio also matters. This ratio compares the size of the brain to the size of the body. It helps adjust for the fact that larger animals need larger brains just to run their basic systems. When you compare species using this ratio, humans have one of the highest scores. This supports the idea that intelligence is not about absolute brain size, but about having more brain relative to what's needed for survival. Even within the human species, brain size varies. But those differences don't predict who will do well in school or who will be creative. A student with a smaller brain might learn a language faster than a classmate with a larger one. An artist might create rich, emotional work without having a high IQ. These differences show that intelligence comes in many forms and doesn't depend on how much brain mass someone has. Modern imaging tools like MRI allow researchers to study the brain in fine detail. They found that the thickness of certain brain areas, the pattern of connections, and the volume of specific regions like the frontal and temporal lobes all play roles in different types of thinking. For example, people with more volume in the left inferior frontal gyrus often do better in language tasks. But again, this is about local structure, not overall size. There's also the issue of plasticity. The brain changes over time. It rewires itself based on what you do, what you learn, and how you live. Someone who trains in math, music, or chess may develop certain brain regions more than others. These changes can improve performance, even if the person starts with a smaller or average brain. The brain grows through use. It's not a fixed tool. Some researchers have studied the link between intelligence and other brain features, like gray matter, which contains most of the brain's neurons. They found that people with more gray matter in certain areas tend to score higher on IQ tests. But again, these are small effects. They help explain part of the picture, not the whole thing. Intelligence is also shaped by genes, environment, and experience. Nutrition, education, and emotional support all influence brain development. A child who grows up in a rich learning environment with supportive adults is more likely to reach their cognitive potential. This happens through brain development and learning, not through changes in size. Many claims about brain size come from outdated or biased studies. In the past, scientists tried to link skull size to intelligence. These studies often ignored key factors like education, social background, and opportunity. Worse, some of them supported harmful racial and gender stereotypes. Today's research takes a more careful approach. It uses better tools and accounts for more variables. In imaging studies with large groups, the correlation between brain volume and intelligence is usually between 0.2 and 0.4. That means brain size explains only about 4 to 16% of the variation in intelligence. Most of what makes someone smart has nothing to do with brain size. It comes from how their brain works, how they use it, and what they do with the knowledge they gain. Think of the brain like a computer. A bigger hard drive doesn't always mean faster performance. What matters more is how the computer is organized, how good the processor is, and how well it runs its programs. In the same way, a bigger brain doesn't guarantee better thinking. Structure, wiring, and use make the real difference. The human brain is complex, and intelligence is even more so. Trying to measure it with a ruler or a scale misses the point. Real insight comes from looking at how the brain functions, not just how big it is. Understanding this helps break down myths and makes room for a more accurate view of how people think, learn, and grow. Many people think that IQ is fixed for life. They believe that intelligence is something you are born with and can never change. Once you take an IQ test and get a score, that number becomes a label. But this view is not supported by science. IQ can shift over time. It changes with environment, education, life experiences, and mental habits. Intelligence is not a static trait. It grows and adapts, especially when challenged. IQ stands for Intelligence Quotient. It's a score based on standardized tests designed to measure a range of thinking skills. These tests include tasks like solving puzzles, recognizing patterns, recalling numbers, and understanding language. They aim to measure cognitive ability, not knowledge. But IQ is only one way to measure intelligence, and it doesn't tell the whole story. The idea that IQ is permanent came from early studies in the 20th century. At that time, psychologists used IQ tests to sort people by ability. Some used it to argue that intelligence was mostly inherited and stable. But later research challenged these claims. Studies began to show that IQ scores could change over time. Children who grew up in better environments often saw their scores improve. Those who faced poverty or poor schooling sometimes showed a decline. IQ can rise or fall depending on what happens in a person's life. Child may score average at age 7, but after years of rich learning and support, score much higher at age 16. Another child may start strong but face challenges that limit learning, illness, trauma, or poor schooling, and score lower later on. These changes don't mean the tests are flawed. They show that the brain and mind are shaped by experience. One large study followed people from childhood into adulthood. Researchers found that some participants showed IQ changes of 15 points or more. That's a full standard deviation. These shifts were linked to changes in the brain. Brain scans showed that increases in IQ scores matched growth in certain brain areas. This finding supports the idea that cognitive ability is flexible, not fixed. Education plays a big role. When children go to school, their thinking improves in measurable ways. They learn to read, solve math problems, think logically, and use language more effectively. All of these skills influence IQ scores. Longer schooling is linked to higher IQs. Programs like early childhood education can raise IQ in young children, especially those from disadvantaged backgrounds. Even short-term programs, if well-designed, can have lasting effects. Mental stimulation also matters. People who read, solve puzzles, learn new skills, or engage in thoughtful conversation tend to maintain or improve their cognitive performance. These activities strengthen the brain's networks and keep them flexible. Just like muscles respond to exercise, the brain responds to effort and challenge. Environment has a clear impact. Children raised in safe, rich environments with books, conversation, and support tend to do better on IQ tests than those raised in stressful or deprived settings. Nutrition, sleep, and access to healthcare also influence brain development. Chronic stress, neglect, or trauma can interfere with cognitive growth, but with the right support, recovery and improvement are possible. IQ is also affected by motivation. In studies where test takers were offered small rewards, their scores improved. This shows that effort plays a part in how well people perform on IQ tests. It's not just about raw ability. It's also about how much you try, how focused you are, and how familiar you are with test taking. Practice makes a difference too. Taking similar tests over time helps people get used to the format. They learn what to expect and how to manage time. This practice can boost scores, even if underlying ability stays the same. But real learning, gaining new ways to think and solve problems, can lead to lasting gains. IQ also shifts with age. Young children often show large changes in IQ scores as their brains develop. In adolescence, the brain goes through major rewiring. Some teens improve in reasoning or memory, while others may struggle for a time. These ups and downs are part of normal development. Even in adulthood, IQ scores can change. Older adults can improve or maintain their abilities by staying mentally and physically active. Some people believe that IQ only goes down with age, but that's not always true. While speed of thinking may slow, vocabulary and knowledge can grow. Many older adults do well on verbal tasks. They may lose speed, but gain depth. They draw on life experience, which is not measured by IQ tests, but matters in real life. IQ is not the same as potential. A person with a lower score can still achieve a high level of skill in a field they care about. Drive, focus, discipline, and creativity all influence what a person can do. IQ tests do not measure those qualities. They also don't measure emotional intelligence, social skills, or moral reasoning. Real-world success depends on more than a test score. Many people with average IQs go on to become leaders, creators, or experts in their fields. They grow by learning, working, and adapting. They build on their strengths and manage their weaknesses. Intelligence is not just what you have, it's what you do with it. Brain plasticity helps explain why IQ can change. The brain keeps forming new connections throughout life. When you learn something new, your brain builds pathways. When you practice a skill, those pathways get stronger. If you stop using them, they weaken. This means that intelligence can be shaped, grown, and refined. It's not set in stone. Some researchers use the term fluid intelligence to describe the ability to solve new problems, and crystallized intelligence to describe learned knowledge. Fluid intelligence tends to peak in early adulthood and then decline. Crystallized intelligence can rise over time. Both types can be influenced by learning and experience. Even fluid intelligence, once thought to be fixed, may improve with certain kinds of training. Working memory training, reasoning exercises, and strategy games have shown promise in some studies. Results vary, and not all training leads to lasting improvement. But some people do show gains in problem solving and attention after focused effort. The brain's capacity to grow and adapt suggests that improvement is possible, especially when practice is sustained. Even mental health can affect IQ. Depression, anxiety, and fatigue can lower performance on cognitive tests. When these issues are treated, thinking often becomes clearer. This shows that temporary factors can change scores. They don't reflect a person's true ability. Treating the whole person, mind, body, and environment helps unlock cognitive potential. IQ is a useful tool in some cases. It can help identify learning needs or track development, but it's not a fixed number that defines a person. It's a snapshot of certain abilities at one point in time. Those abilities can change with care, effort, and support. No single test can capture all the ways a person thinks, learns, or creates. Intelligence is broader than a number. It grows through challenge, practice, and connection with others. The science is clear. IQ is not fixed for life. It moves with the mind that shapes it. The idea that people are either visual, auditory, or kinesthetic learners is widely known and often repeated. Teachers may ask students to take a learning style quiz. Tutors might suggest matching study methods to a preferred style. Some students begin to believe they can only learn in a certain way. But there's a problem with this idea. Research shows no strong scientific support for the theory that matching teaching to a person's learning style improves learning outcomes. People may have preferences, but those preferences do not change how well they learn. The learning styles theory claims that students learn best when taught in a way that matches their preferred sensory mode. Visual learners are said to benefit from pictures and diagrams. Auditory learners are supposed to learn better through listening. Kinesthetic learners, sometimes called tactile learners, are thought to do best with hands-on tasks. The theory sounds logical. It fits with how people describe themselves. But logic and personal belief are not the same as evidence. Over the years, many researchers have tested the learning styles theory. They asked a simple question: does matching instruction to a preferred style help people learn better? The results have not supported the claim. In study after study, teaching in a student's preferred style did not improve test scores, memory, or understanding. In many cases, all students learned better from the same teaching method, regardless of their supposed learning style. One example comes from a controlled experiment. Students took a test to identify their preferred style. Then they were divided into groups. Some were taught in a way that matched their learning style. Others were taught in a different way. All students then took the same test. If the learning styles theory were true, students taught in their preferred style should score higher, but they didn't. Most groups performed about the same, no matter how the lesson was delivered. Another study looked at how students learned science concepts. The researchers used both visual and verbal teaching materials. They found that students learned best when the material fit the subject, not their personal preference. For example, some science topics are best shown with pictures or models, while others are better explained with clear language. This suggests that the nature of the content should guide the method, not the learner's style. Some researchers say the theory is not just unsupported, but misleading. It can give students the wrong idea about how learning works. If a student believes they are only a visual learner, they may avoid other forms of learning. They may ignore spoken explanations or avoid hands-on work. This can limit growth. In reality, effective learning often involves a mix of approaches. Good learners use all their senses when needed. Think of learning to drive. Watching a video might help. Listening to instructions is also useful, but at some point, you need to get behind the wheel and practice. This isn't about matching a learning style, it's about using the right tool for the job. The same applies to most subjects. Reading, listening, watching, discussing, and doing all play roles in learning. Preferences do exist. Some people like to read alone. Others like to hear things explained. These are habits or comfort zones, not hardwired traits. Preference does not equal performance. Just because someone prefers visual input does not mean they learn better that way. In fact, relying on only one mode of learning can hurt performance. Mixing methods, like reading and discussing, can lead to deeper understanding. Another issue is that learning styles are hard to define. Many models exist, and they don't agree. Some list 3 styles, others list 4 or 7. Some include categories like logical, social, or reflective learners. The definitions are vague, and the tests to identify styles are not consistent. A student could take 2 different quizzes and get 2 different results. This makes it hard to use the theory in a reliable way. There is also the problem of labeling. When people believe they have a certain learning style, they may build their identity around it. A student who thinks, "I'm a kinesthetic learner," may avoid reading or listening tasks. They may not even try, believing they will fail. This belief can become a self-fulfilling prophecy. It holds them back, not because they can't learn in another way, but because they don't think they can. Instead of focusing on learning styles, research points to other methods that improve learning. Spaced practice, where you review material over time, helps memory. Retrieval practice, where you quiz yourself, strengthens recall. Interleaving, where you mix different topics or skills, improves understanding. These methods work across different subjects and student types. They are supported by data, not belief. Another effective method is dual coding. This means combining words with visuals. For example, pairing a diagram with a written explanation can help students understand and remember material better. Dual coding works not because it matches a style, but because it gives the brain more ways to connect ideas. It builds stronger memory paths. This method benefits most learners, not just those who say they are visual. Metacognition is also key. This means being aware of how you learn and choosing strategies that fit the task. A good learner can ask, "What is the best way to understand this material?" and then choose the right approach. Sometimes that means watching a video. Sometimes it means taking notes or teaching someone else. Flexibility is better than sticking to one style. Educators can help by teaching students how to learn, not just what to learn. That means showing them how to take good notes, how to ask questions, and how to review material in meaningful ways. It means encouraging them to try different methods and see what works. Instead of asking, "What is your learning style?" teachers can ask, "What strategy will help you learn this material best?" Content should also guide the method. Some information is visual by nature, maps, graphs, charts. Some is verbal, like vocabulary, historical facts, or theories. Some is physical, like sports, art, or lab work. The goal is not to match a method to a person, but to match a method to the subject. Effective teachers do this all the time, often without thinking about learning styles. It's important to base education on evidence, not popular ideas. The learning styles theory has been tested many times. The results are clear. Matching instruction to a learning style does not improve learning. That doesn't mean teachers should ignore differences among students. Students vary in background, interest, and skill. Good teaching meets students where they are, but it does so with flexible strategies, not fixed labels. When students understand that they can learn in many ways, they become more confident. They stop saying, "I can't learn this way," and start asking, "What can I do to understand this better?" They become active learners who take charge of their thinking. This mindset, supported by research, leads to better results than any learning style label. Many people believe they can multitask efficiently. They think they can do 2 or more things at once without losing focus or making mistakes. This idea is especially common in fast-paced environments. Students try to study while texting. Office workers check emails during meetings. Drivers talk on the phone while navigating traffic. The assumption is that the brain can handle all these tasks at the same time. But research shows the opposite. The brain does not multitask in the way most people think. It switches between tasks quickly, and this constant shifting reduces performance and increases errors. The brain has a limited capacity for attention. It can't fully focus on 2 demanding tasks at once. When people think they are multitasking, they are usually task switching. That means they stop one task, shift their focus, and then pick up another. This switch happens fast, sometimes in less than a second, but every switch carries a cost. It takes mental effort to stop one task and start another. That effort adds up. It slows people down and makes their work less accurate. Consider a person trying to write an email while listening to a conference call. The brain must focus on forming words and sentences while also tracking what others are saying. It can't do both at the same time with full attention. What actually happens is the person tunes in and out of the call while typing. As a result, they might miss key points or make typos in the message. Their performance in both tasks suffers. This effect is well documented. In controlled lab settings, psychologists have tested people on tasks that require attention and memory. One classic task is the dual task paradigm. In this setup, participants must respond to 2 different streams of information, often using different rules. The results show that people are slower and less accurate when handling 2 tasks at once compared to doing them separately. The brain needs time to reorient and reset with each switch. The cost of switching tasks is called a switch cost. These costs can show up as delays, confusion, or increased error rates. In some cases, the delays are small, just a few hundred milliseconds. But over time, Those delays add up. They reduce overall productivity and increase mental fatigue. People who multitask often think they are saving time, but studies show they usually take longer to finish their work. Errors are another problem. When switching between tasks, people tend to make more mistakes. They may skip steps, forget important details, or misinterpret information. This happens because attention is split. Working memory, which holds and processes information in the short term, can only handle so much at once. When it's overloaded, it drops information. This leads to slips and errors that could be avoided with focused attention. Driving while using a phone is a well-known example of the dangers of multitasking. Talking on the phone, even hands-free, slows reaction times and increases the chance of accidents. The brain's attention is divided between the conversation and the road. People miss visual cues, drift out of their lane, or take longer to brake. Studies comparing distracted drivers to drunk drivers have found similar impairments in performance. This shows how serious the impact of divided attention can be. Even tasks that seem simple can interfere with each other. Listening to music while reading might not seem demanding, but if the music has lyrics, it competes with the language processing part of the brain. Reading requires focus on words and meaning. Lyrics use the same mental pathways. As a result, comprehension and retention may suffer. Instrumental music may be less disruptive, but even then, it can still pull focus depending on volume, tempo, or personal preference. Some people claim to be super multitaskers, able to handle several tasks at once without any drop in performance. Researchers have tested this idea too. In one study, a small group of people showed better than average performance during multitasking tests. But these individuals were rare, fewer than 3% of the group. Most people, even those who believed they were good at multitasking, performed worse than they thought. This gap between belief and reality is common. People tend to overestimate their ability to manage multiple tasks at once. Age can also play a role. Younger people often feel more confident about switching between tasks. They've grown up with fast technology and constant media. But even among younger adults, multitasking slows performance and increases mistakes. The brain's limits apply regardless of age. In fact, some studies show that frequent multitaskers, especially those who switch between apps, tabs, or devices, perform worse on tests of attention and memory. They struggle more with filtering out distractions and staying on task. The myth of multitasking also affects how people approach work and learning. In schools, students may try to study while watching videos or checking social media. This kind of behavior splits attention and reduces learning. The information may seem to sink in, but recall and understanding drop when tested later. Students may think they are saving time, but the quality of learning suffers. Focused, uninterrupted study sessions are more effective. At work, multitasking can reduce quality and increase stress. Constantly shifting between tasks can leave people feeling mentally drained. It takes more energy to re-engage with a task than to stay with it. This is known as attention residue. Even after switching tasks, the brain holds on to some of the previous task. That residue slows down the new task. Over time, this repeated switching can make it harder to concentrate and easier to burn out. There are ways to work around these limits. One method is time blocking, setting aside specific time slots for specific tasks. This allows the brain to stay focused on one thing at a time. Turning off notifications, closing extra browser tabs, and setting boundaries around screen time can help reduce distractions. Using checklists and breaking tasks into smaller parts can also support better focus. Some tasks do pair well together. Walking while listening to a podcast, for example, can work because walking is mostly automatic. It doesn't take much attention once it becomes a habit. Folding laundry while chatting might be another low-conflict pairing. But even then, if one task suddenly requires more focus, the other may suffer. Knowing when and how to focus is more valuable than trying to juggle too many tasks. The brain works best when it can give its full attention to one thing at a time. While rapid task switching may feel productive, it often reduces quality, slows progress, and increases mistakes. Understanding the limits of attention helps people make better choices about how to manage their time and mental energy. Many people believe that memory works like a video recorder. They picture the brain as a device that captures and stores exact images, sounds, and events from daily life. According to this view, memories play back just as they happened, unchanged and complete. This idea is common in movies, courtrooms, and casual conversations. But research shows that memory does not work this way. Memory is not a perfect recording. It is a reconstruction. Each time you remember something, your brain rebuilds the event using pieces of information. This process is influenced by many factors, including attention, emotion, suggestion, and time. Memory begins with perception. You see, hear, or experience something. Your brain processes that input and stores parts of it. But even at this early stage, memory is selective. You don't store everything. You focus on some details and ignore others. For example, if you're talking to a friend in a busy coffee shop, you may notice their expression and tone, but not the music playing in the background. Your attention shapes what gets stored. After the moment passes, the brain consolidates what it recorded. This process stabilizes memory and moves it from short-term to long-term storage. But even then, the memory is not complete. You remember what stood out, what you focused on, and what made an emotional impact. Many small details never make it into memory at all. Later, when you try to remember the event, your brain does not play back a recording. Instead, it rebuilds the memory using the pieces it stored. It may fill in gaps using logic, related knowledge, or suggestions from others. This makes memory flexible, but it also makes it vulnerable to error. One common example of this is eyewitness testimony. People who witness a crime may feel sure they remember every detail, but studies show that eyewitness memory is often wrong. A person might remember a red car when it was actually blue. They might misidentify a suspect or get the order of events mixed up. These errors aren't lies. The person isn't trying to deceive anyone. Their brain has simply filled in blanks, shifted details, or blended different memories. Research by psychologist Elizabeth Loftus has shown how easy it is to alter memory through suggestion. In one study, participants watched a video of a car accident. Some were asked, "How fast were the cars going when they hit each other?" Others heard, "How fast were the cars going when they smashed into each other?" Those who heard smashed gave higher speed estimates. A week later, they were more likely to say they saw broken glass, even though there was none in the video. The wording of the question changed the memory. Emotion also shapes memory. Strong emotions can make memories feel vivid and real. People often recall where they were during shocking events, a natural disaster, a major news story, or personal trauma. These are called flashbulb memories. They feel accurate and detailed, but even these memories can change over time. People may add or drop details without realizing it. The emotion makes the memory feel certain, but certainty does not mean accuracy. Another factor is time. The longer it's been since the event, the more the memory may fade or shift. The brain updates memories each time you recall them. This process, called reconsolidation, allows memories to change. You might mix parts of two events. You might forget the source of a detail and think it came from your own experience when it didn't. This is known as source confusion. Consider a person remembering a childhood birthday party. They may recall the cake, the guests, and the games. But if they've seen photos of the party or heard stories about it, those may blend with their own memories. They may remember things that never happened or that they didn't notice at the time. Over the years, their memory of the event becomes a mix of fact, suggestion, and imagination. This doesn't mean memory is useless. In most cases, memory serves us well. It helps us learn, make decisions, and carry out daily life. But it's important to understand its limits. People often assume that a confident memory is a reliable one. But confidence does not predict accuracy. Someone can be completely sure of a memory and still be wrong. Memory errors happen to everyone. You might walk into a room and forget why you came. You might think you told someone something when you only thought about it. These are everyday examples of how memory can fail. In more serious cases, memory errors can affect court cases, relationships, and medical treatment. False memories are another sign of how memory is not like a recording. In some experiments, researchers have planted entire memories in people's minds. For example, a person might be led to believe they got lost in a mall as a child, even if it never happened. After hearing the story repeated a few times and being asked to imagine it, the person may remember it with vivid detail. This doesn't mean they are lying. Their brain has built a memory from suggestion, imagination, and belief. Memory also varies from person to person. Some people have strong visual memory. Others rely more on language or emotion. Some can remember lists of facts. Others recall events but forget names. Memory can also be affected by age, stress, sleep, or brain injury. No two people remember things the same way, even if they share the same experience. In conditions like Alzheimer's disease, memory becomes more fragile. People may forget recent events, but remember things from long ago. They may mix up timelines or forget familiar names. This shows how memory is stored and retrieved in complex ways. It's not a single process, and it doesn't always break down evenly. Technology has changed how we think about memory. People now rely on phones, calendars, and the internet to store facts and dates. This can help free up brain space, but it also means people may remember less detail about daily life. The brain doesn't store what it can easily look up. This is called the Google effect. It shows how memory adapts based on how we interact with information. Sleep helps memory. During sleep, the brain consolidates and organizes memories. Without enough sleep, memory becomes less reliable. People may forget details, confuse information, or struggle to learn new things. This is one reason why sleep is important for students and anyone learning new skills. Repetition strengthens memory. When you review material often, you build stronger neural connections. Practice tests, flashcards, and spaced repetition all help. But even repeated memories can change. You may still make errors or fill in gaps without knowing it. That's part of how the system works. The brain does not store experiences like files on a computer. It builds and rebuilds memories using traces, patterns, and associations. This method is powerful and flexible, but not perfect. Memories are shaped by what we pay attention to, how we feel, what others say, and what we believe. They are reconstructions, not recordings. Many people believe that mental decline is a normal and unavoidable part of getting older. They expect memory to fade, thinking to slow down, and learning to become harder. This belief is common and often accepted without question, but research shows that this view is not entirely true. While some changes in the brain do occur with age, mental decline is not automatic. Cognitive function can remain strong well into later life, especially when people stay mentally and physically active. The brain keeps its ability to adapt, learn, and grow even in older adults. Some brain functions do change with age. Processing speed often slows down. This means older adults may take longer to respond to questions or complete tasks that involve new information. Working memory, which helps hold and manipulate short-term information, may also become less efficient. These changes are normal and vary from person to person, but they do not mean that older adults lose their intelligence or ability to think clearly. Other parts of thinking can stay stable or even improve. Vocabulary often increases with age. People continue to gain knowledge and experience throughout their lives. They may become better at understanding language, reading emotions, and making wise decisions. This is sometimes called crystallized intelligence. It reflects the skills and knowledge built up over time. Unlike fluid intelligence, which involves quick thinking and problem solving, crystallized intelligence often grows with age and use. Mental activity plays a big role in maintaining cognitive health. When people challenge their brains regularly, they tend to perform better on memory and thinking tasks. Activities like reading, writing, solving puzzles, or learning a new skill keep the mind engaged. These tasks support attention, reasoning, and memory. They also help build new connections in the brain. This flexibility, known as neuroplasticity, continues throughout life. The brain rewires itself based on what we do and how we use it. Education supports brain health in later years. People with more years of schooling tend to show less cognitive decline. But it's not just formal education that helps. Lifelong learning, whether through books, hobbies, or classes, can also strengthen brain function. Learning to play an instrument, speak a new language, or use new technology challenges the brain in useful ways. These activities keep thinking skills sharp and may even delay the effects of aging. Social interaction also matters. Staying connected with others helps protect against mental decline. Conversations require focus, memory, and quick thinking. Social engagement gives people emotional support and helps reduce stress. Loneliness, on the other hand, has been linked to faster cognitive decline and greater risk of dementia. Regular contact with friends, family, and community groups can keep the brain active and engaged. Physical health affects brain health too. The brain relies on good blood flow, oxygen, and nutrients. Regular physical activity supports all of these. Exercise improves mood, sleep, and energy, all of which support thinking. It also helps reduce the risk of conditions like diabetes, high blood pressure, and heart disease, which can damage brain function over time. Even light physical activity, like walking or stretching, can make a difference. Sleep is another factor. As people age, they often sleep less or wake more during the night. Poor sleep affects memory, attention, and problem solving. Deep, restful sleep helps the brain clear out waste and consolidate memories. Good sleep habits, like keeping a regular schedule, limiting screen time before bed, and avoiding caffeine late in the day, support better thinking and mood. Diet contributes to mental sharpness. The brain needs fuel to function well. A diet rich in fruits, vegetables, whole grains, fish, and healthy fats supports brain health. These foods provide nutrients that help reduce inflammation and protect brain cells. Diets high in processed food, sugar, and saturated fat may increase the risk of cognitive problems. Staying hydrated is also important. Even mild dehydration can affect attention and memory. Mental health also plays a role. Depression, anxiety, and chronic stress can hurt memory and thinking. These conditions are common but treatable. Getting support through counseling, social connection, or medication, when needed, can help protect cognitive function. Reducing stress through techniques like mindfulness, breathing exercises, or time in nature may also support brain health. Dementia is not a normal part of aging. It is a disease, not a natural result of getting older. Most older adults do not develop dementia. Memory lapses, such as forgetting a name or misplacing keys, are common and usually harmless. These small changes do not mean that someone is losing their mind. Dementia involves more serious problems, like getting lost in familiar places or struggling with everyday tasks. It is caused by brain damage and requires medical attention. There is no single test to predict who will experience mental decline. Some people stay mentally sharp into their 90s. Others face challenges earlier. Genetics, lifestyle, and environment all play a role. But choices in diet, exercise, learning, and social activity can influence brain health. People have more control than they may think. One example is the Nun Study, a long-term project that followed aging members of a religious order. Researchers found that nuns who stayed mentally and socially active had better cognitive outcomes, even when their brains showed signs of disease. Their daily routines included reading, writing, prayer, conversation, and reflection. These habits seemed to protect their thinking abilities and help them stay engaged with life. Another example comes from brain training studies. Some adults who practiced specific mental tasks like speed games or memory drills, showed lasting improvements in those areas. While these gains were often narrow, they showed that the brain can respond to challenge. Other studies suggest that real-world learning, like managing finances or planning travel, can support broad thinking skills. People who stay curious often do better mentally. Curiosity leads to exploration and learning. It keeps the brain alert and adaptable. Trying new activities, asking questions, and reflecting on experiences all support mental growth. Curiosity can be sparked by a wide range of interests, from gardening to history to technology. Routine also helps. Having a daily schedule supports memory and reduces stress. It allows the brain to focus on important tasks without wasting energy on small decisions. Routines that include exercise, learning, social time, and rest provide structure and balance. Staying mentally sharp is not about avoiding aging. It's about how people respond to it. Some changes in thinking are normal, but many can be managed or slowed. The brain can stay active, creative, and capable long after retirement. It responds to use. Just like muscles need movement, the brain needs challenge. Cognitive function in older age depends on many small habits built over time. Staying physically active, mentally engaged, socially connected, and emotionally healthy helps protect the brain. These habits don't require special training or expensive programs. They rely on regular choices: what to eat, how to move, when to rest, and what to learn. Mental decline is not written in stone. While some change is expected, much of it can be slowed or prevented. The brain continues to learn and adapt at every age. With care, attention, and effort, people can stay mentally strong well into later life. Many people believe that humans fall into one of two groups: emotional or rational. Emotional people are seen as driven by feelings, prone to snap judgments, and less likely to think things through. Rational people are viewed as cool-headed, guided by facts, and less affected by emotion. This split between heart and mind shows up in everyday speech, in books, and in movies. But brain science tells a different story. Emotion and logic are not separate forces pulling in opposite directions. They are deeply connected. Most decisions involve both. Emotions shape how we think, and reasoning depends on the input emotions provide. The idea that emotion blocks reason is old. Philosophers like Plato wrote about the struggle between reason and passion. That idea stayed strong for centuries. But it doesn't match what we know about the brain. The brain is not split into a logic center and a feeling center that fight each other. Instead, emotional and cognitive processes work together. They influence each other constantly. One key example comes from the work of neuroscientist Antonio Damasio. He studied patients who had damage to a part of the brain called the ventromedial prefrontal cortex. These patients could think clearly and perform well on logic tests, but they struggled with real-world decisions. They couldn't weigh risk, consider long-term outcomes, or choose between options. They lacked the emotional signals that help people make choices. Without emotion, they were stuck. Their reasoning worked, but they couldn't apply it in a useful way. This shows that emotion plays a key role in judgment and decision-making. Feelings help people sort information. In any moment, the brain receives more input than it can fully process. Emotions act as a filter. They signal what matters and what doesn't. A feeling of fear draws attention to danger. A sense of joy pulls focus toward a rewarding outcome. Even small preferences, liking one color more than another, can help narrow down choices. Without these emotional cues, decision-making becomes harder, not easier. Emotions also help people learn. When something good or bad happens, the emotional response marks the memory. That signal tells the brain, "This is important, remember it." This process helps build experience and guides future choices. A child who touches a hot stove feels pain and learns not to do it again. The pain adds weight to the memory. A student who feels proud after solving a problem is more likely to enjoy learning. The positive feeling reinforces the behavior. Even logic depends on emotional input. Consider a person making a financial choice. They gather facts, weigh risks, and plan for the future. That process seems purely rational. But underneath, emotions play a role. Fear may steer them away from risky options. Hope may push them toward long-term gains. Regret from past mistakes may shape how they handle current challenges. Their decision isn't just about numbers. It's about how they feel about those numbers. In the courtroom, jurors are told to be rational and base their decision only on evidence. But lawyers know that emotion matters. A skilled lawyer presents a case that appeals to both logic and feeling. A jury may believe the facts, but it's the emotional impact, the story, the tone, the expression, that often tips the scale. People don't separate logic and emotion when deciding what is true or fair. They use both. In marketing, the same pattern appears. Companies don't just list product features. They appeal to feelings: comfort, safety, belonging, status. Even when shoppers compare prices or read reviews, their final decision often rests on how they feel about the brand or the product. Rational analysis plays a part, but emotion drives action. Brain imaging studies confirm this. When people make decisions, areas of the brain involved in both reasoning and emotion light up. The prefrontal cortex handles planning and logic. The amygdala and other limbic areas process emotion. These regions talk to each other. The flow of information goes both ways. Reasoning shapes how we feel. Feelings shape how we think. Neither system works in isolation. Personality also affects how people use emotion and logic. Some people are more aware of their feelings. They might say they follow their gut. Others like to list pros and cons. But even the most analytical person still uses emotion. They may not notice it, but it's there. A strong desire for accuracy, a dislike of being wrong, or a relief that comes with a clear answer. All these are emotional reactions that affect how they process information. People also adjust their thinking based on the situation. In a crisis, emotion often comes first. In a calm setting, there may be more time to reflect. But even fast decisions have some basis in past experience, and that experience is stored with emotional tags. A firefighter who senses danger in a burning building may not be able to explain why. Their body reacts before they've worked through the logic. That reaction is based on years of training, shaped by emotion and memory. Another example is parenting. A parent might decide how to discipline a child. They may feel frustrated, but they know that yelling won't help. They pause, take a breath, and choose a different response. That choice involves both emotional awareness and rational thought. The emotion is not ignored, it's managed and included in the process. Teaching emotional skills can help people think more clearly. Emotional intelligence includes self-awareness, self-regulation, empathy, and social skills. These traits support better decision-making. When people understand their feelings and how they affect their thoughts, they make more informed choices. They're less likely to act on impulse and more likely to pause, reflect, and respond with care. In conflict, emotions run high. People may say things they later regret, but understanding those emotions can lead to better outcomes. If two people disagree and one of them feels unheard, that feeling may block logical discussion. But if the other person acknowledges the emotion, the conversation can move forward. Emotions don't block reason. They signal where attention is needed. Emotions also support moral reasoning. People decide what is right or wrong based on a mix of principles and feelings. A sense's guilt may steer someone away from harmful actions. Compassion may push them to help others. These are not signs of weakness. They are signs that emotion is part of ethical thought. Some people believe that removing emotion leads to better thinking. They try to stay neutral, detached, and cold. But detachment has limits. Without emotional input, decisions may lack empathy or meaning. they may miss the human side of a problem. In many cases, the best outcomes come from integrating emotion and reason, not from choosing one over the other. People are not just emotional or rational, they are both. The brain evolved to use emotion and logic together. Separating them does not reflect how thinking works. It limits understanding. Emotions guide thought. Thought shapes emotion. Together, they help people learn, decide, and grow. Many people have heard that mental illness is caused by a chemical imbalance in the brain. This idea shows up in public service messages, doctor visits, and even conversations between friends. It sounds simple and easy to understand. According to this view, conditions like depression or anxiety happen because the brain lacks the right amount of certain chemicals, such as serotonin or dopamine. If you take medication that adjusts those levels, the illness goes away. This explanation helped reduce stigma in some ways. It shifted blame away from the person and toward biology. But the truth is more complex. Mental illness cannot be reduced to just a chemical imbalance. The brain is a complex organ. It contains billions of neurons that send signals to one another through electrical impulses and chemicals called neurotransmitters. Serotonin, dopamine, norepinephrine, and other chemicals help regulate mood, attention, sleep, and motivation. They play roles in mental health, but they do not tell the whole story. Most mental health conditions involve changes across many systems in the brain and body. These include genetics, brain structure, life experience, stress, sleep, relationships, and behavior. Depression is a good example. Early research suggested that people with depression had low serotonin levels. This led to the idea of a serotonin deficiency. Drugs called SSRIs, selective serotonin reuptake inhibitors, were developed to raise serotonin levels. These medications became common. Many people who took them felt better. That seemed to support the chemical imbalance theory. But later studies showed that the relationship between serotonin and depression is not that simple. Some people with depression have normal serotonin levels. Others have high levels. SSRIs help some people, but not others. The drugs often take weeks to show results, even though they change serotonin levels within hours. This delay suggests that the medication may be working through other systems. Some researchers believe that the real benefit comes from how the brain adapts to the medication over time, rather than just the immediate chemical changes. Brain imaging studies show that depression involves changes in brain activity and connectivity. Areas like the prefrontal cortex and amygdala show different patterns of activation in people with depression. These areas affect emotion, decision-making, and attention. Stress, trauma, and loss can affect how these brain regions function. Genetics also play a role. People with a family history of depression are more likely to experience it themselves. But even then, genes are not destiny. Life experience and coping skills influence how genes express themselves. Social factors matter too. Loneliness, financial stress, discrimination, or ongoing conflict can raise the risk of mental illness. These experiences can lead to changes in thinking, behavior, and even the brain. For example, chronic stress affects the hypothalamic pituitary adrenal (HPA) axis. This system controls how the body responds to stress. When it becomes overactive, it can lead to problems with mood, energy, and sleep. These are common symptoms in depression and anxiety. Sleep plays a key role. Many people with depression report problems falling or staying asleep. Poor sleep can worsen mood and thinking. Over time, it can affect hormone levels, attention, and memory. Addressing sleep problems often improves mental health. This shows how biological, behavioral, and environmental factors interact. Physical activity is another piece. Exercise improves mood and lowers anxiety for many people. It boosts levels of brain-derived neurotrophic factor, BDNF, a protein that supports brain growth and plasticity. It also helps regulate neurotransmitters and reduces inflammation. These effects go beyond simple chemical balance. They show how behavior influences biology. Therapy works too, even without changing brain chemistry directly. Approaches like cognitive behavioral therapy, CBT, help people notice and change patterns of thought and action. This can reduce symptoms and build coping skills. Brain scans show that therapy can change activity in key brain regions, just like medication. This suggests that talk therapy and drugs may work through different paths to support brain health. Other forms of treatment, like mindfulness and meditation, also affect brain structure and function. Studies show that regular mindfulness practice can change the thickness of certain brain regions and reduce symptoms of anxiety and depression. Again, these changes are not just about chemicals. They involve attention, focus, and emotional regulation. Diet also plays a role. Some evidence links poor nutrition with a higher risk of depression. Diets high in processed foods, sugar, and unhealthy fats may increase inflammation, which affects brain function. In contrast, diets rich in fruits, vegetables, whole grains, and healthy fats support brain health. Some studies show that dietary changes can reduce symptoms of depression, especially in people with poor eating habits. Relationships matter. People with strong social support tend to have better mental health. Connection provides safety, feedback, and emotional comfort. Isolation increases risk. Support from family, friends, or support groups can help people manage stress and feel less alone. These effects are hard to reduce to a single chemical or brain region. Even beliefs and expectations influence outcomes. Some people improve after taking a placebo, a pill with no active drug, simply because they believe it will help. Placebo effects involve real changes in brain chemistry and function. This shows that hope, trust, and mindset play roles in how treatment works. The chemical imbalance theory may have helped people understand that mental illness is not a personal failure, but it also oversimplifies the problem and the solution. It may lead people to believe that pills alone can fix complex conditions. In reality, most people benefit from a mix of treatments, including medication, therapy, lifestyle changes, and social support. What works best varies from person to person. Mental illness is not a single cause, and it doesn't have a single fix. It arises from a web of factors: brain chemistry, genes, stress, habits, relationships, and meaning. These pieces interact in ways we are still learning to understand. Treatments that focus on just one part of the system may miss important opportunities to help. A narrow focus on chemicals can also ignore the role of trauma and life experience. People who grow up in unstable or violent homes may carry the effects for decades. They may develop patterns of fear, distrust, or hopelessness. These are not caused by low serotonin. They reflect learned responses to a harsh world. Healing in these cases often requires safety, trust, and new ways of relating to others, not just medication. The brain is flexible. It responds to experience, choice, and change. People with mental illness are not broken or chemically flawed. They are often facing difficult challenges that affect how they feel and function. Support, understanding, and access to a range of treatments can help. The goal is not to fix a broken brain, but to support a person in rebuilding health, meaning, and connection. Simplifying mental illness to a chemical imbalance does not do justice to the full experience. It risks limiting care to one option. Mental health is personal, complex, and shaped by many forces. A broader view allows for better care and greater respect for the human experience. Many people believe that left-handed people are more creative. This idea appears in books, news articles, and casual conversation. People often point to famous left-handed artists, writers, and musicians, like Leonardo da Vinci, Pablo Picasso, or Jimi Hendrix as proof. The belief has a strong appeal. It suggests that left-handedness gives people special access to creativity and imagination. But the scientific evidence for this link is mixed. Some studies show small differences. Others find none. There is no strong, consistent support for the idea that left-handed people are more creative than right-handed people. Handedness refers to the hand a person prefers to use for tasks like writing, eating, or throwing. About 90% of people are right-handed. The rest are left-handed or use both hands for different tasks. This preference is tied to how the brain organizes movement. Each side of the brain controls the opposite side of the body. So right-handed people usually have stronger motor control in the left hemisphere. Left-handed people often show more variation in how their brain is organized. The idea that left-handed people are more creative is based in part on brain lateralization. Some functions, like language, are usually located more on one side of the brain. For most right-handed people, language centers are on the left side. Some researchers have suggested that left-handed people may have more balanced or flexible brain activity between the two hemispheres. This balance could allow for different kinds of thinking. In theory, this might support creativity, but research does not offer a clear answer. Some studies show that left-handed people score slightly higher on tests of divergent thinking. These tests measure how many ideas a person can generate in response to a prompt. For example, a test might ask someone to list as many uses as possible for a paperclip. People who list more varied responses are thought to be better at divergent thinking. A few studies have found that left-handed or mixed-handed people produce more ideas on these tasks. Other studies, though, do not find such differences. Many show no link between handedness and creativity scores. In some cases, right-handed people score higher. In others, there is no pattern at all. When researchers combine the results of many studies, the overall effect is small or non-existent. This suggests that handedness alone is not a reliable marker of creativity. Creativity itself is hard to define and measure. It includes many skills such as originality, problem-solving, artistic talent, and innovation. People can show creativity in art, science, business, or everyday life. Some people create music. Others design buildings, write stories, or invent tools. No single test can capture all the ways people express creativity. This makes it harder to link creativity to traits like handedness. History offers many examples of creative people from all sides of the handedness spectrum. Leonardo da Vinci was left-handed and known for his wide-ranging genius. So was Paul McCartney, who wrote some of the most famous songs of the 20th century. But Isaac Newton, Jane Austen, and Ludwig van Beethoven were right-handed and also highly creative. The same is true today. Many modern artists, inventors, and writers are right-handed. Handedness does not seem to limit or unlock creative ability. Another challenge is that handedness is not a simple trait. Some people are strongly right or left-handed. Others are more flexible. They may write with one hand, but throw a ball with the other. Some researchers study degree of handedness, how strong a person's preference is, rather than direction. A few studies have found that people with less consistent handedness perform better on certain creative tasks. They may be more comfortable switching between mental strategies. But again, these effects are small and not always found in new studies. There are also social and cultural factors. In the past, left-handed people were often forced to switch to using their right hand. This was common in schools and families, especially during the early and mid-20th century. As a result, older generations may underreport left-handedness. In some cultures, left-handedness is still discouraged. These pressures can affect how researchers study handedness and may hide the true range of variation. Being left-handed can bring both advantages and challenges. In some sports, like tennis or boxing, left-handed players may have an edge because opponents are less used to facing them. In design, left-handed people often have to adapt to tools and spaces made for right-handed users. This constant adjustment may build flexibility and problem-solving skills, but it's not clear that these challenges lead to higher creativity. Adaptability and resilience may grow through experience, but they are not limited to one group. Some studies look at the link between handedness and mental health. Left-handed people may show slightly higher rates of certain conditions, like dyslexia or ADHD. but the differences are small and not well understood. These patterns may reflect differences in brain development. Still, most left-handed people do not have mental health problems, and most people with these conditions are right-handed. There is no clear link between left-handedness and mental illness, nor between mental illness and creativity. The media often highlights unusual traits of famous people. If a well-known artist or musician is left-handed, that fact may be mentioned in articles or biographies. Over time, these stories shape public belief. People start to see a pattern, even when it may not exist. This is a kind of confirmation bias. We notice the examples that fit the idea and ignore the ones that don't. This makes the left-handed creativity link seem stronger than it really is. It's also possible that creativity shapes how people use their hands. Some artists or musicians may train themselves to use both hands, depending on the task. Ambidexterity, using both hands with equal skill, is rare, but some creative people may develop it through practice. In this case, the handedness may result from the creative work, not cause it. In education, it's important not to assume that handedness tells us much about a student's potential. Teachers should support all learners and offer different ways to explore ideas. Creativity can be encouraged through open-ended projects, problem-solving tasks, and space for personal expression. It doesn't depend on which hand a student writes with. In work and life, creativity grows through experience, curiosity, and effort. People become more creative by trying new things, taking risks, and learning from mistakes. Brain structure and handedness may play small roles, but they do not define a person's creative ability. What matters more is what people do with their time, attention, and energy. The belief that left-handed people are more creative has a long history, and it's not without some evidence. But the evidence is mixed, and the effect is small at best. Most creativity research points to a wide mix of traits, habits, and skills that support creative thinking. These include openness to experience, mental flexibility, and persistence. They are not tied to handedness in a clear or consistent way. Creativity is a broad and complex trait that cannot be predicted by hand preference alone. Many people assume that more brain activity means better thinking. The idea seems to make sense. If the brain is working harder, it must be doing more. When we'll see brain scans with glowing areas of activation, it's easy to believe that more activity equals more intelligence or stronger mental performance. But this belief doesn't hold up under scientific scrutiny. In many cases, better thinking involves less activity, not more. A well-trained, efficient brain often uses less energy to perform the same task. It works smarter, not harder. The brain uses a lot of energy. It makes up about 2% of body weight, but consumes around 20% of the body's energy at rest. That energy goes toward maintaining communication between neurons, supporting brain cells, and keeping networks ready to respond. When you start a mental task, solving a problem, reading, or remembering something, certain areas of the brain become more active. They increase energy use and blood flow. Functional MRI scans can detect these changes and show which regions light up. But more activity on a scan doesn't always mean better performance. It often means the brain is working harder to complete a task it hasn't mastered. When a person is new to a skill, they use more brain regions. They may involve areas that handle attention, control, or working memory. As they improve, the brain becomes more focused. It uses fewer regions. Pathways become faster, more direct, and more specialized. The person performs better, even though brain activity looks lower. One example is learning to play an instrument. A beginner pianist may show widespread brain activity while practicing scales. They need to focus on finger movement, reading music, and timing. Their brain calls on multiple networks to manage all the pieces. An experienced player, on the other hand, shows more focused activity. Their brain has built strong, efficient pathways. It no longer needs to recruit extra help. It does more with less. The same pattern appears in math. Novice problem solvers often show more activation in frontal regions tied to effort and control. Experts show more activity in areas tied to memory and automation. The shift reflects a change from effortful processing to fluent performance. The expert may think more clearly and make fewer errors, even though their brain scan looks calmer. This idea is known as neural efficiency. It suggests that smarter or more experienced brains use energy more efficiently. They don't waste effort. Instead of lighting up the whole system, they activate only the areas they need. This concept has support in research on intelligence. Some studies show that people with higher IQs often show less brain activity during certain tasks. Their brains may be better at filtering information, managing attention, and skipping unnecessary steps. Neural efficiency doesn't mean no effort. It means targeted effort. When a task is complex or unfamiliar, even an efficient brain needs to work hard. But it works hard in a smarter way. It focuses energy where it counts. This allows for faster response, better accuracy, and less mental fatigue. It also explains why some people appear calm in high-pressure situations. Their brain is not in overdrive. It's using well-practiced strategies. A skilled public speaker may look relaxed on stage. Inside, their brain is following familiar patterns. They have trained those circuits. A nervous beginner may use more brain power just to stay focused. Their mental energy is spread thin across too many demands. Brain imaging studies also show that practice changes how the brain works. In memory tasks, repeated practice reduces the load on the prefrontal cortex. This region helps with attention and control. As tasks become automatic, the need for conscious control drops. The brain shifts the work to other areas that handle routine processing. This switch frees up resources for new challenges. Athletes show similar patterns. When learning a new move, they activate more brain regions, including those related to planning and correction. With training, the brain shifts control to motor regions. Movements become faster and more fluid. Coaches may say the athlete is thinking less during the action. That's accurate in a way. The brain has streamlined the process. Efficient brains also manage distractions better. When working on a task, people with higher mental focus show less activity in the default mode network. This network becomes active during rest or daydreaming. Turning it down during a task helps keep attention steady. Efficient brains are better at this switch. They direct energy toward the task and away from unrelated thoughts. In contrast, more activity can sometimes signal confusion, stress, or overload. A student cramming for a test may light up many brain regions, but still struggle to recall information. Their brain is trying hard, but not working efficiently. A better approach, spaced repetition, review, and rest, would lead to stronger performance and less mental strain. Efficiency also depends on the match between the brain and the task. A person may show strong efficiency in one area, like music or math, but not in another. The brain's networks develop through experience and interest. That means no one has a generally efficient brain. Instead, we all build areas of strength through use, repetition, and feedback. The idea that more brain activity is always better can lead to confusion in public understanding. It may cause people to chase brain training apps or supplements that promise to boost brain power, but performance depends more on how well the brain is trained for specific tasks than on how much activity it shows. Learning, practice, rest, and focus build stronger pathways. They improve function without needing to increase overall brain energy use. This idea also applies to education and work. Encouraging students to think more doesn't mean pushing them to work harder all the time. It means helping them find better strategies. Teaching people how to focus, break problems into parts, and check their work builds efficiency. These habits allow for better thinking with less effort. In the workplace, long hours and multitasking can drive up mental effort but lower quality. When the brain is stretched too thin, it becomes less efficient. Mistakes increase, memory slips, and judgment declines. Taking breaks, focusing on one task at a time, and building clear systems help people think more clearly and work more effectively. Mental health also affects efficiency. Anxiety, depression, and fatigue can make the brain work harder to perform basic tasks. This added load reduces capacity for complex thinking. Treatment and support can restore efficiency and improve performance without requiring more mental energy. The brain is not like a car engine that works better the more it revs. It's more like a computer that performs best when it uses only the resources it needs. Efficient thinking involves streamlined pathways, clear strategies, and strong habits. It's the product of learning, practice, and care. It doesn't always look dramatic. Often, it looks quiet, calm, and focused. More brain activity may look impressive on a scan, but in many cases, better thinking shows up as less, not more, neural effort. Many people believe that listening to Mozart can make you smarter. This idea became popular in the 1990s and led to a wide range of claims. Parents played Mozart for their babies. Schools and companies used classical music to boost performance. Music CDs promised cognitive benefits just from pressing play. This belief, known as the Mozart Effect, suggested that listening to certain types of music could improve intelligence, especially in young children. But the evidence behind this claim does not support such a strong conclusion. The real effects of music on thinking are more modest and temporary. Listening to Mozart may help boost alertness or mood, but it does not increase intelligence in any lasting or meaningful way. The original study that started the Mozart Effect was published in 1993. Researchers asked college students to listen to a Mozart sonata before taking a spatial reasoning test. The results showed a small improvement in test scores right after listening to the music. This improvement lasted only about 10 to 15 minutes. The researchers did not claim that listening to Mozart raised intelligence or had long-term effects. They suggested that music might temporarily enhance performance on certain types of tasks that used spatial skills. But the media picked up the story and ran with it. Headlines claimed that Mozart made people smarter. The idea spread fast. It was simple, appealing, and easy to act on. Playing music is low-cost and non-invasive. Parents and teachers hoped it would give children an edge. The state of Georgia even started giving classical music CDs to new parents. But later studies did not support the hype. When other researchers tried to repeat the Mozart study, they found mixed results. Some saw small effects, others saw none. Some found that any kind of music, classical or not, could produce a similar short-term boost. Others found that silence or a few minutes of rest could be just as effective. When researchers looked at the full set of studies, they found that the original effects were small, brief, and not specific to Mozart. What likely happened in the original study is related to arousal and mood. Music can make people feel more alert, awake, or focused. This state of increased arousal may help with performance on simple mental tasks. It's not about raising intelligence. It's about creating a mental state that supports short-term performance. Many types of music can do this. For some people, Mozart helps. For others, it might be pop, jazz, or even silence, depending on what helps them focus. This explanation makes sense based on what we know about attention and performance. When people feel good, they often perform better. A positive mood can improve concentration and memory. A brief mental break or a few minutes of enjoyable music can reset the mind and reduce stress. These changes can lead to better results on short tasks, but they do not increase raw intelligence or ability. It's also important to understand what intelligence means in this context. Intelligence is not one thing. It includes many skills: verbal ability, problem solving, spatial reasoning, memory, attention, and more. IQ tests try to measure these skills, but they are not perfect. A single short-term change on one part of one test does not mean someone is smarter overall. Some studies suggest that musical training, not just listening, may have long-term benefits. Learning to play an instrument engages many parts of the brain. It involves memory, coordination, attention, and emotion. Over time, musical training may help with skills that also support learning and thinking. Children who study music often do better in school, but that may reflect broader support from family, school, or personality. These students may already have traits that support success, such as discipline, patience, or curiosity. Listening to music, on the other hand, is passive. It may influence mood, but it doesn't require effort or learning. There's no strong evidence that listening to Mozart or any other composer boosts intelligence on its own. That doesn't mean music has no value. Music can lift mood, reduce stress, and bring people together. It can support mental health, focus, and relaxation. These benefits matter, but they are not the same as becoming smarter. The popularity of the Mozart Effect may reflect a deeper wish. People want easy ways to improve learning and intelligence. They want solutions that don't require major changes, but lasting improvement usually comes from effort, practice, feedback, and persistence. There are no shortcuts to complex thinking. Music may help create a better environment for learning, but it's not a substitute for study, engagement, or skill development. Other myths have followed a similar path. Claims that brain training games make you smarter, or that certain foods unlock potential, often rely on small studies or out-of-context results. They may work in narrow ways, for short periods, but they don't deliver broad or lasting cognitive gains. Real gains come from building habits over time. Reading, writing, exercise, and challenge support brain health in ways that are grounded in evidence. Music still has a place in learning environments. Playing music in classrooms or study spaces can help set a tone, reduce anxiety, or support focus. But the type of music, volume, and timing all matter. For tasks that require focus, instrumental music at low volume often works best. Lyrics or loud beats can distract. For breaks or relaxation, more upbeat music might help. The key is to find what works for each person and task. Music therapy is another area where research is ongoing. For people with certain health conditions, including dementia or stroke, music can help with mood, memory, and movement. In these settings, music is part of a structured plan. It's not about boosting IQ, but supporting well-being and function. Even though the Mozart Effect doesn't live up to the hype, the story has value. It reminds us to look closely at claims about brain science. Not all studies say what headlines suggest. It's easy to misinterpret findings or overstate effects. Critical thinking helps us sort useful ideas from overblown ones. Music is powerful, but not magical. Listening to Mozart won't raise your IQ, make your child a genius, or replace effort, but it can bring joy, improve mood, and help set the stage for focused work. Those effects matter in daily life. They support learning indirectly, not by changing intelligence, but by improving the mental state that supports thinking. That's a valuable role, even if it's not the one the original myth promised. Many people worry that smartphones are rewiring our brains in dangerous ways. They hear claims that constant scrolling shortens attention spans, weakens memory, and damages deep thinking. These ideas appear in books, opinion pieces, and social media posts. Some suggest that smartphone use is changing the brain itself, causing permanent harm. But these claims often go beyond what the evidence shows. Technology does affect the way we think, focus, and relate to others. But the effects are not necessarily dangerous or irreversible. The brain is flexible. It adapts to new tools and environments. That is not new and not always bad. Smartphones have changed how people access information, stay connected, and spend their time. They offer maps, reminders, messaging, entertainment, and more. These tools shape habits. People often reach for their phone during idle moments. They check it during meals, in waiting rooms, or before bed. This behavior affects attention. It trains the brain to expect quick rewards and constant input. Over time, it may become harder to stay focused on one task for long periods. But this is about habit, not damage. Attention is a skill that can be trained and improved. Some studies show that heavy smartphone use is linked to shorter attention spans. People who check their phone often may have more trouble staying focused on a reading task or a lecture. But cause and effect are hard to prove. It's possible that people who already struggle with attention are drawn to frequent phone use. The relationship may go both ways. Also, the brain is capable of shifting gears. When people set limits, change habits, or use apps more deliberately, attention improves. The fear that smartphones are rewiring the brain often comes from a misunderstanding of what brain plasticity means. Plasticity refers to the brain's ability to change in response to experience. It's how people learn new skills, recover from injury, or adapt to new environments. All learning changes the brain in some way. Reading, driving, playing music, or using tools all reshape neural pathways. So do digital devices. But not all change is harmful. The brain adapts to what people do most. If someone spends more time reading books, their brain strengthens certain networks. If someone practices using maps or doing mental math less often, those skills may weaken. But that doesn't mean they're lost forever. Memory is another area of concern. People often rely on their phones to store facts, dates, and directions. This can make it harder to recall information on their own. But researchers call this the Google Effect, and it's not entirely negative. The brain offloads information to tools so it can focus on other things. This is called transactive memory, sharing the work of memory with external systems. Before smartphones, people used address books, calendars, or other people to help remember. Outsourcing some memory allows space for problem solving, planning, and analysis. It's true that relying too much on external tools can reduce practice in certain skills. If someone never tries to remember phone numbers or directions, those abilities may fade. But like muscle strength, memory can be rebuilt with use. There is no sign that smartphones cause permanent damage to memory systems. When people engage in tasks that require recall, they can still perform well. The key is to balance convenience with challenge. Using the phone as a tool doesn't mean avoiding mental effort completely. Social behavior is also shaped by smartphone use. Many people stay in touch with family, friends, and coworkers through texting, voice messages, or apps. This expands connection across distance. But it also changes how people interact face-to-face. Some studies show that phone presence during conversations reduces the sense of connection and engagement. People may feel distracted or less understood. This doesn't mean smartphones ruin relationships, but it highlights the importance of mindful use. Turning off notifications, setting boundaries, or putting the phone away during meals can improve the quality of interactions. Sleep is another area where smartphones have an effect. Many people use their phone late at night. The light from screens can delay the release of melatonin, a hormone that helps people fall asleep. Scrolling through apps or checking messages before bed can also keep the mind active when it should be winding down. Over time, poor sleep affects memory, mood, and attention. These effects are well documented, but they're not unique to smartphones. Any light, noise, or stimulation before sleep can interfere with rest. Creating a regular bedtime routine, reducing screen use at night, and keeping the phone out of the bedroom can help. Young people often draw the most concern. Parents worry that growing up with screens will harm their children's brain development. But the research in this area is still developing. Some studies suggest that high levels of screen time are linked to lower academic performance or social skills. Others find no strong effect. Content and context matter. Educational apps, creative projects, or positive social interaction can support learning and development. Passive use, such as endless scrolling or background noise, may offer fewer benefits. The same is true for adults. How people use technology often matters more than how much they use it. It's easy to blame new tools for changes in thinking or behavior, but the human brain has always adapted to new technology. When writing became common, some people feared it would weaken memory. When television spread, others worried it would reduce attention. The printing press, the radio, and the internet all sparked concern. But people adapted, new habits formed, skills shifted. The same process is happening with smartphones. Technology brings trade-offs. It offers speed, access, and connection, but it can also distract, overwhelm, or replace certain mental habits. The goal is not to fear change, but to manage it. People can build digital habits that support focus, health, and relationships. Setting time limits, turning off non-essential alerts, and making space for deep work or rest are practical steps. Choosing when and how to use a phone gives people more control. The brain responds to these choices. It builds pathways based on what people do again and again. The concern that smartphones are rewiring the brain in dangerous ways oversimplifies the issue. The brain changes with experience, but change is not the same as damage. People can adjust how they use technology and regain focus, memory, or calm. These abilities are not lost. They respond to training, just like before. Understanding how technology affects the brain allows people to make better decisions, not out of fear, but with purpose. Smartphones are tools. Like any tool, they can help or hinder, depending on how they're used. The brain adapts, and people can too. Many people believe that screen time causes ADHD. They point to children who spend hours on phones, tablets, or video games, and then struggle to focus in school or at home. The behavior looks like classic signs of attention deficit hyperactivity disorder: short attention span, restlessness, impulsivity. Because these signs often show up in heavy media users, people assume that screen use must be the cause. But the science does not support this idea. Screen time does not cause ADHD. The disorder has biological roots. It involves differences in brain development, genetics, and behavior regulation. While too much screen use may make symptoms worse, it does not create the condition itself. ADHD is a neurodevelopmental disorder. It affects how the brain develops and manages attention, impulse control, and activity levels. People with ADHD often have trouble focusing, staying still, following instructions, or waiting their turn. These challenges show up in many parts of life, including school, work, and relationships. ADHD begins in childhood and can continue into adulthood. The symptoms must be present before age 12 and must cause problems in at least 2 settings, such as home and school. Research shows that ADHD runs in families. It has a strong genetic component. Brain scans reveal differences in structure and function, especially in areas related to attention, planning, and self-control. These brain differences affect how signals move through networks that support thinking and behavior. They are not caused by watching TV or using a phone. They are present from an early age, before most children have regular access to screens. Still, screen use can affect how symptoms show up. Children with ADHD may be drawn to fast-paced, high-stimulation content. Games and videos that offer constant rewards and rapid feedback can hold their attention longer than schoolwork or chores. These media experiences are designed to be engaging. They use color, sound, movement, and instant feedback to keep users involved. For someone with ADHD, this kind of stimulation may feel easier to focus on than tasks that require sustained effort or delayed rewards. This doesn't mean screens cause ADHD. It means that children with ADHD may use screens differently. They may find screen-based activities more rewarding and struggle more when asked to switch to low-stimulation tasks. This can make the gap between screen time and other parts of life feel wider. Parents may see a child focus for hours on a game, but lose interest in reading after 5 minutes. That difference is frustrating, but it reflects how ADHD affects motivation and reward systems, not a result of screen exposure itself. Some studies do find a link between heavy screen use and attention problems. Children and teens who spend more time on screens may show more signs of inattention, irritability, or restlessness. But correlation is not causation. These patterns don't prove that screen time creates the symptoms. It's just as likely that children who already have attention issues are drawn to media that matches their pace and preferences. In many cases, screen use is a coping tool, not a cause. One study followed adolescents who used multiple forms of media, texting, social media, video games, and found a small increase in attention difficulties over time. But the changes were small, and the study relied on self-reports. It could not separate pre-existing traits from media effects. Other studies find no link between screen time and ADHD symptoms when controlling for factors like sleep, family stress, or parenting style. These results suggest that screen use may play a role, but it is only one part of a much larger picture. Sleep is one area where screen habits can influence ADHD symptoms. Many children and teens use screens late at night. The blue light from screens can delay melatonin release, making it harder to fall asleep. Poor sleep worsens attention, mood, and self-control. For children with ADHD, lack of sleep can make symptoms more noticeable. Reducing screen time before bed often helps with sleep and, in turn, improves daily behavior. But the issue here is sleep quality, not the screen itself. Parenting also shapes how children respond to screen time. Clear rules, routines, and consistent expectations help all children, especially those with ADHD. When screen use is unregulated, children may struggle more with transitions, limits, or self-control. This can make symptoms worse, even if the screens are not the original problem. Setting limits on screen time, encouraging outdoor play, and offering structured routines can support better focus and behavior. Treatments for ADHD include behavior therapy, parent training, school support, and sometimes medication. These approaches target the core symptoms and help children develop better self-regulation. In some cases, technology can support these goals. Apps that guide routines, timers that help with focus, and educational games can offer useful tools. The key is how the technology is used. Passive consumption of endless content may not help, but active tools that support goals can be part of a helpful plan. It's also important to consider content. Not all screen time is the same. Watching fast-cut videos filled with flashing lights is not the same as reading a digital book, talking to a friend over video chat, or building a city in a game that requires planning and patience. Context and purpose matter. Some screen-based tasks support thinking, creativity, and focus. Others offer distraction and escape. Knowing the difference can help families make better choices. Adults with ADHD also show similar patterns. Many report using screens to manage mood, pass time, or avoid difficult tasks. They may lose track of time while scrolling or gaming. But structured use of technology, such as setting timers, using task lists, or blocking distracting sites, can support focus and reduce stress. These tools don't fix ADHD, but they can help people manage it. Blaming screens for ADHD distracts from more important work. It can increase guilt among parents who are already trying their best. It can also lead to fear-based rules that don't help children learn how to manage media in real life. A better approach is to understand how ADHD affects motivation, focus, and behavior, and to use that understanding to guide screen use. Children with ADHD benefit from structure, clear feedback, and consistent support. Media can be part of that support when used with intention. That might mean watching a documentary together, using an app to support homework, or playing a cooperative game that builds social skills. What matters most is not how many minutes a child spends on a screen, but what they do during that time and how it fits into their larger routine. ADHD is a real, brain-based condition with complex causes. Screen time does not cause it, but screens can affect how symptoms show up and how children manage them. By setting healthy limits, choosing quality content, and focusing on sleep and routines, families can reduce the negative effects of screen use. And by understanding ADHD as more than just behavior, parents and educators can better support the children in their care. The goal is not to eliminate screens, but to use them in ways that help rather than hinder. With care and structure, screen time can be managed without fear or blame. Many people believe that brain training apps can make them smarter. These apps promise to improve memory, focus, problem solving, and even overall intelligence. They offer short games and tasks that target skills like attention, speed, and pattern recognition. Some even claim to reduce the effects of aging or prevent cognitive decline. The idea is appealing. You spend a few minutes a day playing a game, and your brain gets stronger, like a muscle at the gym. But research shows that these claims are often overhyped. Brain training apps may improve performance on the specific tasks they teach, but they rarely boost general intelligence or real-world thinking. The main idea behind brain training is that the brain can improve through repeated mental practice. That much is true. The brain is flexible and adapts to experience. This quality, called neuroplasticity, is real. If you practice something every day, you usually get better at it. But the key question is whether those gains transfer to other tasks. In other words, does getting better at a memory game help you remember your grocery list, learn a new language, or focus during a meeting? Studies show that brain training apps do lead to better performance on the games themselves. If you play a pattern recognition task every day, you will improve at that task. Your speed, accuracy, and confidence may increase, but that improvement tends to stay within the game. When researchers test whether those gains apply to other skills, like reading comprehension, math ability, or fluid reasoning, the results are much weaker. Fluid reasoning refers to the ability to solve new problems, make decisions, and apply logic without relying on memorized knowledge. It's a core part of what people call intelligence. If a brain training app really improved fluid reasoning, it would help in a wide range of situations. But most apps do not show strong or consistent effects in this area. In studies where participants used brain training apps for weeks or months, researchers found little to no improvement in general cognitive ability compared to control groups. One well-known study tested the effects of brain training on thousands of adults. Some participants used brain training games for several weeks. Others did unrelated tasks. When tested afterward, both groups showed similar improvements on general thinking tasks. The training helped people get better at what they practiced, but it didn't lead to broad gains. This suggests that the benefits of brain training are narrow, not wide. Some companies have made strong claims about their apps. One major company promoted its program as a way to improve attention and delay cognitive decline. But in 2016, the U.S. Federal Trade Commission fined the company for deceptive advertising. The claims went beyond what the evidence supported. Since then, other companies have taken a more cautious approach, but the belief that brain training can raise intelligence is still common. Age can affect how people respond to brain training. Older adults may see small benefits in memory or attention from using certain programs. But again, the gains tend to stay close to the tasks practiced. For example, an older adult who plays a digit-span game may get better at recalling sequences of numbers, but that doesn't mean they'll remember names or appointments more easily. These skills use similar brain systems but are not the same. For children, the picture is also mixed. Some studies suggest that targeted training in working memory can help certain students, especially those with attention challenges. But the effects are often small and don't last long. If a child struggles with math, playing a brain game may not improve their math performance unless the game is directly related to math skills. Real learning often comes from instruction, feedback, and practice in the subject itself. That doesn't mean brain training is useless. It can be fun and engaging. For some people, it offers a structured way to challenge their mind and stay mentally active. It may help build confidence or reduce boredom. These effects matter. They can support mental well-being, but they don't mean that a person is becoming smarter in a broad sense. It also helps to compare brain training to other mental activities. Reading, playing a musical instrument, learning a new language, or solving real-world problems all involve complex thinking. These activities build knowledge, memory, and focus in meaningful ways. They often engage multiple brain systems at once. They also lead to skills that are useful outside the activity itself. For example, learning a new language may improve memory, attention, and cultural awareness. These gains are more likely to transfer than gains from a simple reaction time game. Social interaction also supports brain health. Conversations require attention, memory, and flexibility. They involve listening, forming responses, and managing emotion. These demands exercise the brain in real time. Staying socially connected has been linked to lower risk of cognitive decline in older adults. It's a form of mental stimulation that comes with real-world meaning. Physical activity supports brain function too. Exercise improves blood flow to the brain and supports the growth of new neural connections. It also improves mood, sleep, and stress regulation, all of which affect thinking. People who exercise regularly often show better attention and memory. These effects are well documented. Sleep plays a key role as well. During sleep, the brain consolidates memory, clears waste, and resets attention systems. Poor sleep affects thinking, learning, and mood. No brain training app can replace the benefits of deep, restful sleep. The same is true for diet. A balanced diet supports brain health by providing the nutrients needed for brain function. These include healthy fats, antioxidants, and vitamins. If someone enjoys brain training apps and finds them useful, there's no harm in using them. But it's important to keep expectations in check. These games are like drills. They train specific skills in a limited way. They are not magic tools for boosting intelligence. Improving thinking skills takes time, effort, and a variety of experiences. Reading deeply, solving real problems, talking with others, and staying physically active all support strong thinking. These habits are more likely to lead to lasting benefits than tapping through levels on a screen. The brain responds to what it does most. If a person spends time learning, practicing, reflecting, and connecting, the brain adapts to support those activities. If someone only trains with narrow tasks, the brain gets better at those tasks. That's how learning works. Brain training apps follow the same rule. They help most with the specific tasks they target. If those tasks match a person's goals, the apps may be useful. But if the goal is to become smarter in general, the best path still runs through reading, problem-solving, movement, rest, and connection. Those habits build a brain ready to learn, adapt, and think clearly across many areas of life. Many people believe that we'll soon be able to upload consciousness to computers. This idea appears in science fiction, popular science books, and tech conferences. Some imagine a future where minds live forever in digital form. Others picture a version of themselves backed up like files on a hard drive. The basic claim is that if we can scan the brain closely enough, we can copy it into a computer and keep thinking without a biological body. But current neuroscience does not support this as a near-term reality. The idea is speculative and faces major scientific and technical barriers. Consciousness is not just memory or data. It includes awareness, emotion, experience, and a sense of self. It's not clear how these elements arise from brain activity, let alone how to capture and recreate them in another medium. The brain is made of about 86 billion neurons. Each neuron connects to thousands of others through synapses. These networks form the basis of thought and experience. But the brain is not just a map of connections. It also includes chemical signals, electrical activity, and dynamic changes over time. Some researchers suggest that if we could record the structure of every neuron and synapse in a brain, we might be able to recreate how that brain processes information. This process is called whole brain emulation. In theory, a computer model based on this map could run the same patterns and produce the same responses. That model might act and talk like the original person. But this approach makes big assumptions. It assumes that brain structure alone is enough to reproduce consciousness. It assumes that everything important about a person can be captured in a static map. These assumptions are far from proven. We still don't know how the brain produces consciousness. Scientists can study the brain's activity, identify regions involved in attention, emotion, or language, and track changes in brain states. But we don't have a clear explanation for how subjective experience arises. We don't know why certain patterns of activity feel like anything at all. This problem, often called the hard problem of consciousness, remains unsolved. Without understanding how consciousness works, it's risky to assume we can copy it. Even mapping the brain in full detail is far beyond current tools. The Human Connectome Project, for example, aims to map large-scale brain connections using imaging methods like fMRI. But these methods lack the resolution to capture individual neurons or synapses. Higher resolution tools exist, but they work on tiny slices of tissue and take enormous time and effort. Mapping 1 cubic millimeter of brain tissue at synapse-level detail can take months or years and produce petabytes of data. Scaling that up to the entire brain is a massive technical challenge. The brain is also alive and dynamic. Neurons fire, grow, die, and change connections over time. Chemicals flow, signals fluctuate, experience shapes the system. To capture consciousness, it might not be enough to record structure. We may also need to capture the state of the system at a specific moment, including patterns of activity, neurotransmitter levels, and other factors. This snapshot would need to include not only where everything is, but how everything is behaving at that moment. Even if we could capture that snapshot, running it in a computer poses more problems. The brain operates in parallel, with many processes happening at once. It's not clear how to replicate that on digital hardware. Computers process information differently than brains. They run on different principles. Software designed to imitate the brain may not recreate its full function. And even if the system behaves in familiar ways, talking, responding, showing memory, there's no guarantee it would be conscious. It might be a simulation without experience. Some people argue that if a system acts like a person, we should treat it as conscious. Others say that true consciousness requires more than behavior. It may require a specific kind of system or material. For example, some theories suggest that consciousness depends on biological features that can't be duplicated in silicon. These theories propose that neurons are not just switches, but special cells with properties that matter for awareness. If that's true, then copying structure won't be enough. There are also ethical questions. If we could create a conscious digital mind, would it have rights? Could it suffer? Could it choose to stop existing? If we copied someone's mind, would the copy be the same person or just a duplicate? Would the original person survive, or would they still die while a version of them lived on? These questions don't have clear answers, but they matter for anyone considering this path. Some people hope brain uploading could lead to digital immortality. They imagine a future where minds live in virtual worlds, free from disease or aging. This idea is attractive, especially to people facing illness or loss. But it depends on solving many hard problems that remain open. Today, the tools we have are not close to supporting full brain emulation or digital consciousness. That said, neuroscience and computing are advancing. Researchers are building detailed models of small neural circuits. They're studying brain-computer interfaces that allow people to control devices with thought. These tools offer real benefits, especially for people with movement or communication challenges. They show that the brain and machines can work together, but they do not point toward uploading minds. Machine learning has also advanced. Some systems can now imitate human speech, writing, or decision-making. These tools may seem intelligent, but they are not conscious. They do not have beliefs, goals, or experiences. They work by finding patterns in data, not by understanding or feeling. The gap between this kind of processing and human consciousness remains wide. Public interest in brain uploading often runs ahead of the science. Tech companies may promote bold visions of the future to attract attention or funding. Media coverage may repeat these claims without checking the evidence. But scientific progress depends on careful testing and clear definitions. Right now, the idea of uploading a mind is more of a philosophical question than a technical plan. Even if uploading were possible someday, it might not work the way people expect. A digital mind might not feel the same. It might lack a body, senses, or social context. Those features shape human thought in deep ways. The self is not just a brain. It is a person in a world shaped by movement, feeling, and tender self and interaction. For now, the best way to support the brain is to care for the person. Healthy sleep, good food, physical activity, learning, and connection all support brain function. These habits help people think clearly, remember well, and feel grounded. They are available now and based on strong evidence. Uploading consciousness to computers remains a far-off idea. It depends on solving deep questions in neuroscience, ethics, and engineering. It's not impossible, but it's not close. Today's understanding of the brain does not support it as a near-term goal. The brain is not a simple machine, and the mind is not just code. Efforts to copy consciousness must grapple with the full depth of what it means to be alive and aware. Some people believe that artificial intelligence can fully replicate the human brain. They see advances in machine learning, natural language processing, and robotics and assume we're close to building systems that think and feel like humans. AI can now write essays, answer questions, drive cars, and translate languages. These tools seem intelligent on the surface. They often perform better than humans at specific tasks, but that doesn't mean they match the full scope of human thought. Today's AI systems do not replicate the human brain. They mimic some of its functions, but they fall short of human consciousness, emotion, and awareness. The brain is a biological organ made up of about 86 billion neurons. These neurons form complex networks that support perception, memory, decision-making, movement, and emotion. The brain does not just compute. It senses, moves, feels, and responds to the world in real time. It changes with experience. It supports imagination, attention, and social understanding. It operates through chemical signals, electrical impulses, and feedback loops. These features work together to create a sense of self, a sense of others, and an awareness of the world. AI systems do not operate in the same way. Most are built on algorithms that process inputs and generate outputs based on rules or statistical patterns. Large language models, for example, learn by analyzing massive amounts of text. They identify patterns in word use and use those patterns to generate plausible responses. These systems don't understand meaning the way humans do. They don't have beliefs, goals, or memories shaped by lived experience. They do not perceive the world or reflect on their place in it. Their output may look human, but the process behind it is different. A human child learns language through interaction. They link words to objects, actions, and feelings. They build a model of the world through play, emotion, and feedback. Language is not just a pattern. It's a tool for expression, connection, and thinking. AI models learn language by processing text. They don't form concepts or connect words to sensory experience. They don't understand the difference between truth and fiction unless programmed to track it. Their responses are based on probability, not insight. The human brain also supports emotion. Feelings shape attention, memory, and decision-making. They guide behavior and relationships. The brain integrates emotion with logic, drawing on past experience and bodily signals. AI systems do not feel. They may detect emotional tone in text or mimic an emotional response, but they don't experience joy, fear, or regret. This matters. Emotion is not extra, it's central to how humans think and act. Humans also think across time. They remember the past, imagine the future, and form a sense of continuity. They reflect on values, choices, and goals. They have a personal history and a concept of self that shapes how they think. AI systems do not have this. They process each task in isolation unless given a memory system. Even then, the memory is not like human memory. It stores data but does not shape identity. AI does not reflect, doubt, or grow in the human sense. Some people argue that with enough data and processing power, AI could eventually match the brain. But it's not just a matter of scale. The brain is not just big, it's structured in a way that supports adaptation, emotion, and meaning. Its processes are deeply embedded in a living body and shaped by the physical and social world. Current AI does not have a body in the same way. It does not sense heat, pain, balance, or hunger. It does not form attachments or habits. These gaps are not minor. They define the difference between mimicry and understanding. For example, a robot may detect objects and avoid collisions, but it doesn't care whether it breaks or succeeds. It doesn't learn from pain or reward in the way a human does. It may adjust its behavior, but it does not build preferences or values. It does not seek out comfort or connection. Without these drives, its decisions are functional, not personal. In some cases, AI outperforms humans. It may analyze patterns faster, solve math problems without error, or sift through large datasets. But this speed does not imply general intelligence. It reflects narrow skill in well-defined tasks. Humans are general thinkers. They can apply knowledge across domains, adapt to new situations, and solve problems creatively. They use context, emotion, and prior experience in ways that current AI cannot. Some researchers focus on building artificial general intelligence, or AGI. The goal is to create machines that can perform any intellectual task a human can. But even among experts, there is little agreement on how to define AGI or how close we are to it. Some say it may arrive within decades. Others believe it could take centuries or may never happen. The gap between current AI and full human-level thinking remains large. Brain-inspired models, such as neural networks, take some ideas from neuroscience. They include layers of nodes that mimic the way neurons activate in response to input. But even these models are only loosely based on biology. They simplify how neurons behave and do not capture the full richness of brain activity. For instance, real neurons fire with complex timing and interact with many types of chemical signals. Real brains also include glial cells, blood flow, and dynamic changes that current models do not replicate. Neuroscience still does not fully understand how the brain supports consciousness. Researchers know which regions are active during certain tasks. They can trace circuits involved in vision, movement, and language. But the exact mechanism that gives rise to awareness remains unknown. Without that knowledge, it's hard to know what it would take to build a conscious machine. Some systems can simulate conversation well enough to fool people in short exchanges. But passing a test like the Turing test, where a machine imitates human responses, does not prove true understanding. Deception is not the same as consciousness. A chatbot may answer questions smoothly, but have no awareness of the topic or even the conversation itself. Real intelligence involves more than responding to input. It includes curiosity, doubt, hope, and growth. It includes making mistakes, learning from them, and changing. It includes choosing values and facing trade-offs. These elements shape human thinking in ways that go beyond computation. AI will continue to improve. It will assist with diagnosis, planning, design, and many other tasks. It may help people learn, build, and solve problems more effectively. But that doesn't mean it will become human. Its strengths and weaknesses are different. Knowing the limits of AI helps people use it wisely. It also protects against false assumptions. Thinking clearly about what AI can and cannot do matters for science, ethics, and public trust. Right now, no machine replicates the full range of human thought. AI systems perform specific tasks using rules and patterns. They do not feel, reflect, or grow in the way people do. The human brain remains unmatched in complexity, nuance, and consciousness. AI tools may continue to evolve, but their path is not the same as the one followed by living minds. For many years, people believed that you were born with all the brain cells you will ever have. This idea came from early neuroscience research, which suggested that once the brain developed in childhood, it stopped producing new neurons. Scientists thought the adult brain could grow new connections between cells, but not new cells themselves. According to that view, brain development was a one-time event. After that, any damage or loss was permanent. But research over the last few decades has shown that this belief is not true. The adult brain can and does make new neurons, especially in areas involved in learning and memory. This process is called neurogenesis. It refers to the birth of new neurons from neural stem cells. These stem cells are a type of cell that can divide and become specialized brain cells. In adults, most neurogenesis happens in a part of the brain called the hippocampus. The hippocampus plays a major role in forming new memories, processing spatial information, and supporting flexible thinking. It's also one of the first brain regions affected in Alzheimer's disease. Scientists first saw evidence of adult neurogenesis in animals. In the 1960s, researchers found dividing cells in the brains of rats. Later studies confirmed that new neurons were forming in the hippocampus of adult rodents, birds, and monkeys. These findings changed how scientists thought about the brain's ability to renew itself. Still, there was debate over whether humans showed the same pattern. In the 1990s, researchers found evidence of neurogenesis in adult human brains. They used a special technique that involved a compound called bromodioxyuridine, or BRDU, which labels dividing cells. This method allowed scientists to see that new neurons were forming in adult brains, especially in the hippocampus. Later studies used other methods, including carbon dating and imaging tools, to track new brain cell growth in living people and in donated brain tissue. These discoveries don't mean the brain makes new neurons everywhere or in large numbers. Neurogenesis is limited to specific areas and tends to slow down with age. Most of the brain's growth after birth comes from forming new connections, not new cells. But even a small number of new neurons can have a big impact, especially in regions where learning and memory happen. These new cells can become part of active networks and support mental flexibility. The rate of neurogenesis is not fixed. It changes based on what a person does and experiences. Physical exercise, especially aerobic activities like walking or running, can increase the birth of new neurons in the hippocampus. In animal studies, rodents that had access to running wheels showed more neurogenesis than those that didn't. In people, exercise has been linked to improved memory and increased volume in the hippocampus, suggesting a similar effect. Learning and environmental stimulation also support neurogenesis. When animals explore new environments or face cognitive challenges, they tend to produce more new neurons. In humans, mental activities like reading, solving problems, or learning new skills may have similar effects. These activities don't just keep the mind sharp, they may help grow it in small but meaningful ways. Stress, on the other hand, can reduce neurogenesis. Chronic stress increases the release of cortisol, a hormone that affects many body systems, including the brain. High levels of cortisol can shrink the hippocampus and reduce the birth of new neurons. This may partly explain why long-term stress is linked to memory problems and mood disorders. Managing stress through sleep, social support, physical activity, or therapy may help protect the brain's ability to renew itself. Diet also plays a role. Foods rich in omega-3 fatty acids, antioxidants, and flavonoids, such as fish, berries, and leafy greens, may support brain health and cell growth. A diet high in processed food or sugar may do the opposite. Some studies also suggest that intermittent fasting or calorie restriction may support neurogenesis, though these ideas are still being tested in humans. Not all researchers agree on the extent of neurogenesis in adults. Some recent studies have questioned whether new neurons continue to form in the adult human hippocampus, especially in older adults. These studies used different tissue samples and methods and found lower levels of new neurons than earlier research. But other studies have responded with evidence that neurogenesis does continue, though at a lower rate than in youth. The debate is ongoing, but most researchers agree that at least some neurogenesis takes place in adults and plays a role in learning and memory. Whether or not new neurons are created in large numbers, the adult brain remains dynamic. Even if cell birth slows, the brain constantly changes its connections in response to experience. This is called synaptic plasticity. It allows the brain to adapt, learn, and recover from injury. Neurogenesis adds another layer to this flexibility. It shows that the adult brain is not a finished product, but an active system that responds to what we do and how we live. This has important implications for mental health. In depression, the hippocampus often shrinks, and neurogenesis may slow. Some antidepressants seem to support neurogenesis, which may partly explain their effects. Understanding how new neurons form and function may lead to new treatments for mood disorders, cognitive decline, and brain injury. But this work is still in progress. Scientists continue to study how these new cells integrate into brain networks and what factors influence their survival. The belief that we are born with all our brain cells is based on old science. It underestimates the brain's ability to adapt and grow. While most brain development happens early in life, the process does not stop at birth. The brain continues to change throughout adulthood. New neurons are part of that story. They form in response to movement, learning, environment, and lifestyle. They may not be the only way the brain grows, but they show that change is still possible. This does not mean we can regenerate the brain at will. Most brain cells are not replaced, and large-scale damage is still hard to repair. But the existence of adult neurogenesis adds hope. It means the brain is more flexible than once thought. It also shows that daily choices about movement, stress, rest, and challenge affect not just how we feel, but how our brain works and grows. The science continues to evolve, but the core message is clear. The brain is not fixed at birth, and we do keep making some of our own brain cells, even as adults. The idea that alcohol kills brain cells is common and often repeated. Many people grow up hearing that every drink destroys part of their brain. The image is simple and alarming. You drink and neurons die. But this idea doesn't match what the science shows. Moderate alcohol use does not kill brain cells. Long-term alcohol abuse, however, can damage brain structure and function in other ways. The full picture is more complex than a blanket statement about cell death. The human brain is made of billions of neurons. These cells communicate through electrical and chemical signals. They support memory, movement, emotion, and thought. Brain cells are delicate, and they rely on stable conditions to work well. Because of this, it makes sense to worry about what alcohol might do. Alcohol is a central nervous system depressant. It slows down brain activity, affects coordination, lowers inhibition, and impairs judgment. These effects are clear even after 1 or 2 drinks. But they reflect changes in signaling, not cell death. In moderate amounts, alcohol does not kill neurons. That's been shown in both human and animal studies. When scientists examine brain tissue from people who drink occasionally or in small amounts, they do not see signs of neuron loss. Instead, the short-term effects of alcohol come from changes in how neurons communicate. Alcohol affects the release of neurotransmitters like GABA and glutamate. It alters how neurons respond, which changes behavior and thought for a short time. But those neurons recover once the alcohol leaves the system. Heavy or chronic alcohol use is a different story. When people drink large amounts over time, the brain can show signs of shrinkage, especially in the frontal lobes and cerebellum. These areas help control decision-making, movement, and emotion. Imaging studies of long-term heavy drinkers often show a loss of brain volume. This shrinkage may be partly due to the loss of white matter, the insulation that helps signals travel through the brain efficiently. But even here, actual neuron death is limited. The damage tends to involve changes in structure and function, not widespread destruction of brain cells. One condition linked to long-term alcohol abuse is Wernicke-Korsakoff syndrome. It's a type of brain damage caused by a severe lack of thiamine, or vitamin B1. This vitamin is essential for brain energy use. People who drink heavily for long periods often have poor diets, and alcohol interferes with vitamin absorption. When thiamine levels drop too low, parts of the brain can break down, leading to memory problems, confusion, and coordination issues. In this case, the damage is real and lasting, but the cause is not alcohol killing neurons directly. It's malnutrition caused by alcohol abuse. Alcohol can also affect the developing brain more severely. In fetuses, alcohol can interfere with normal brain development. This is known as fetal alcohol spectrum disorder. It can lead to lasting problems with learning, attention, and behavior. In teenagers and young adults, whose brains are still developing, heavy drinking may interfere with the growth of key brain regions. But again, the effect is not simple neuron death. It's a disruption of development, signaling, and connectivity. Another concern is how alcohol affects neurogenesis, the process by which the brain creates new neurons. Most adult neurogenesis happens in the hippocampus, a region important for memory and learning. Some studies show that heavy drinking can reduce the birth of new neurons in this area. That may explain why long-term alcohol abuse is linked to memory problems and trouble learning new things. This effect may be reversible if drinking stops and other brain-supportive habits are added, but it highlights how alcohol can affect brain health in ways beyond killing cells. Moderate drinking means different things in different studies, but a common definition is up to 1 drink per day for women and up to 2 for men. At these levels, there's no strong evidence of brain damage. Some research even suggests that light to moderate drinking, especially of red wine, may be linked to lower rates of cognitive decline in older adults. This could be due to social interaction, relaxation, or compounds in wine like resveratrol. Still, these findings are mixed, and the potential benefits must be weighed against other health risks. Alcohol use becomes more dangerous when it turns into dependence. People with alcohol use disorder often lose control over their drinking. They may need more alcohol to feel the same effects. They may drink to avoid withdrawal symptoms like anxiety, tremors, or seizures. Over time, their tolerance builds, but the brain becomes more sensitive to alcohol's harmful effects. The cycle of abuse, withdrawal, and relapse puts stress on the entire nervous system. Withdrawal itself can harm the brain. In severe cases, sudden stopping after heavy use can cause seizures or delirium tremens. These conditions can damage brain cells if not treated. That's why medical supervision is often needed when someone stops drinking after long-term use. The effects of alcohol also vary based on genetics, age, sex, and health status. Some people may be more vulnerable to alcohol's effects on the brain. For example, women tend to reach higher blood alcohol levels than men after drinking the same amount. This may make them more prone to brain changes with heavy drinking. Older adults may also be more sensitive to alcohol's effects, especially if they take medications or have other health issues. Even when alcohol doesn't kill neurons, it can still impair brain function. After a night of heavy drinking, most people feel foggy, tired, or slow. This is not brain death. It's the temporary result of how alcohol affects brain chemistry, hydration, and sleep. But over time, repeated episodes of heavy drinking can build up and affect brain performance. There's also a social factor to consider. Drinking in moderation often happens in social settings, dinners, celebrations, or gatherings. Social engagement supports brain health. People who feel connected tend to have lower rates of depression and cognitive decline. But drinking too much can also lead to isolation, conflict, or risky behavior. These outcomes harm brain health indirectly through stress, injury, or emotional strain. So while the image of alcohol burning brain cells might be simple and scary, it's not accurate. A glass of wine or a beer doesn't kill neurons. Even a night of heavy drinking won't wipe out brain cells like a fire. But long-term, excessive use can change how the brain works. It can shrink brain regions, block new cell growth, and interfere with memory and thinking. The damage comes from disruption, not destruction. Understanding the true effects of alcohol helps people make informed choices. It removes fear-based myths and replaces them with facts. Alcohol affects the brain, but not always in the way people think. The key is to know how much is too much, how often is too often, and how personal habits affect brain health over time. With that knowledge, it becomes easier to enjoy life while protecting the brain's ability to think, learn, and grow. People often hear that the brain has two sides, a logical left side and a creative right side, and that each side works separately. This idea shows up in books, personality quizzes, classroom posters, and even job interviews. It's an easy concept to understand. If you're good at math, you're left-brained. If you're artistic, you're right-brained. But this view doesn't match what neuroscience shows. The brain does have two hemispheres, and certain functions are more active on one side than the other. But the two sides are deeply connected. They work together through a structure called the corpus callosum, which allows them to share information constantly. The brain is divided into left and right hemispheres. Each controls the opposite side of the body. The left hemisphere mainly manages the right side of the body, while the right hemisphere controls the left. This is why a stroke on the left side of the brain can lead to weakness or paralysis on the right side of the body. This kind of control is clear and well documented, but motor control is just one example of lateralization, the idea that certain brain functions are more dominant in one hemisphere than the other. Some functions do show patterns of lateralization. In most right-handed people, the left hemisphere plays a larger role in language. Areas like Broca's area and Wernicke's area, both found in the left hemisphere, help with producing and understanding speech. But that doesn't mean the right hemisphere does nothing with language. It helps with tone, rhythm, and the emotional side of speech. It supports understanding jokes, sarcasm, and figurative language. If the left hemisphere is damaged, the right side may help fill in some language functions over time. It's not as efficient, but it can adapt. The right hemisphere often takes the lead in spatial processing. It helps with tasks like reading maps, recognizing faces, and understanding shapes. But the left hemisphere still contributes to these skills, especially when they involve sequences or patterns. For example, solving a puzzle or drawing a picture usually involves both sides of the brain. You use the right hemisphere to see the big picture and the left to notice details or follow steps. These two sides work best when they work together. The corpus callosum plays a major role in this teamwork. It's a thick bundle of nerve fibers that connects the two hemispheres. It allows information to pass back and forth in milliseconds. This connection supports almost every mental task you do: speaking, reading, driving, making decisions, or even daydreaming. Without the corpus callosum, the two sides of the brain can't communicate as well, and strange things can happen. Studies of people who had their corpus callosum cut, usually as a treatment for severe epilepsy, offer a window into how the two hemispheres interact. These split-brain patients can often function normally in daily life, but they show unusual behavior during tests. For example, if you show an image to only the left visual field, processed by the right hemisphere, a split-brain patient may not be able to say what they saw. That's because the right hemisphere saw the image, but the left hemisphere, which controls language in most people, didn't get the message. However, the patient might still be able to draw the object with their left hand, which the right hemisphere controls. These cases reveal how each side can work on its own, but also how limited that work becomes without communication between the two. In healthy brains, the two sides stay in constant communication. Even simple tasks like naming a color or recognizing a voice draw on systems spread across both hemispheres. Brain scans show that when people read, solve math problems, or play music, both sides light up. The activity may be stronger in one hemisphere, but the other side still contributes. That's how the brain handles complex problems. It pulls from different regions and coordinates their efforts. The myth of separate left and right brain personalities likely grew out of these early studies on lateralization. When researchers saw that language tended to live in the left hemisphere and visual tasks in the right, people made broad generalizations. They assumed logical thinking must come from the left brain and creative thinking from the right. Over time, this turned into a cultural shorthand. Left-brained people are rational. Right-brained people are artistic. But this leap goes far beyond what the science supports. Creativity and logic both use many parts of the brain. Writing a story, for example, calls on memory, language, emotion, planning, and imagery. Solving a math problem may involve logic, but it can also require visualizing patterns or thinking flexibly. These processes do not sit in one half of the brain. They rely on networks that cross the midline and involve both hemispheres. Personality also cannot be traced to one side of the brain. Traits like introversion, openness, or emotional sensitivity do not belong to a specific hemisphere. They reflect many factors, including genetics, environment, life experience, and brain chemistry. Studies of personality using brain imaging show activity in many areas: frontal lobes, limbic system, and more, not a single side. In classrooms and workplaces, the left brain, right brain myth can be misleading. It may cause people to limit themselves or make assumptions about others. A student who believes they are not a math person because they're more right-brained may avoid subjects they could actually do well in with practice. A job candidate labeled as too analytical or too creative may face unfair expectations. Real learning and problem solving use all parts of the brain, depending on the task and the person's strategy. Understanding how the two hemispheres work together helps build a more accurate view of the brain. It also opens the door to better teaching, therapy, and self-understanding. For example, stroke rehabilitation often involves training the undamaged hemisphere to support lost functions. Music therapy may help language recovery by tapping into right hemisphere systems that support rhythm and tone. These treatments work not because one side replaces the other, but because the brain is adaptable and interconnected. In summary, the two hemispheres of the brain are not completely separate in function. They each have strengths, and some tasks do rely more on one side than the other. But for most daily activities, both sides of the brain work together, linked by the corpus callosum. The idea of strictly left-brained or right-brained people is a myth. The truth is more balanced and more interesting. The brain is a cooperative system, and its power comes from that integration. People often hear that the brain is gray. Diagrams show it as gray. Textbooks describe gray matter and stop there. Even phrases like gray matter between your ears support the idea. But this is only partly true. The brain does contain gray matter, but it also contains white matter and pinkish, blood-rich tissue. These parts work together and serve different functions. To understand how the brain works, it helps to know what these parts are and why they matter. Gray matter refers to areas of the brain packed with neuron cell bodies. These regions handle processing and decision-making. When you think, remember, plan, or feel, gray matter does much of the work. It's dense with neurons and supporting cells. In a fresh brain, gray matter has a pink-gray color because of blood and tissue makeup. When preserved for study, the tissue often looks duller and more clearly gray, which may explain how the idea took hold. The outer layer of the brain, the cerebral cortex, is mostly gray matter. It's the wrinkled surface that covers the brain's hemispheres. This cortex plays a role in higher-level tasks like language, attention, problem-solving, and social thinking. Under a microscope, it looks grainy and full of small cells with branching shapes. These are the neurons that send and receive signals. Around them are glial cells that support and protect neurons, helping them do their work. Gray matter is not limited to the surface. Deeper inside the brain, structures like the thalamus, basal ganglia, and hippocampus also contain gray matter. These regions help with movement control, sensory input, memory, and emotional regulation. When these areas are damaged, people may struggle with memory loss, tremors, or emotional swings. This shows how central gray matter is to core brain function. But the brain would not work well if it were only made of gray matter. Neurons need to send messages across long distances. That's where white matter comes in. White matter consists mainly of myelinated axons. Axons are the long, thin parts of neurons that carry electrical signals. Myelin is a fatty coating that wraps around axons and helps signals travel faster and more efficiently. It gives white matter its pale, whitish appearance. White matter acts like wiring between regions of gray matter. It connects different brain areas and allows them to communicate. For example, when you hear a word and then repeat it, gray matter in your auditory cortex processes the sound, and white matter pathways carry that information to your speech centers. Without those connections, your brain regions would work in isolation. You might understand a word but not be able to say it. One major white matter structure is the corpus callosum. It connects the left and right hemispheres and lets them share information. Another key area is the internal capsule, which carries signals between the cortex and the spinal cord. Damage to white matter can slow thinking, reduce coordination, or interrupt communication between brain areas. In multiple sclerosis, for example, the immune system attacks myelin. This disrupts white matter and leads to symptoms like weakness, vision problems, or difficulty walking. Both gray and white matter are essential. They have different jobs but rely on each other. Gray matter processes information, while white matter moves it around. In healthy brains, these systems are balanced. During development, white matter increases as axons grow and myelinate. In aging, both gray and white matter may shrink, but changes in white matter are often more closely tied to cognitive decline. Then there's the pinkish color of the living brain. A fresh brain isn't truly gray or white. It has a warm tone due to its rich blood supply and living tissue. Arteries and capillaries bring oxygen and nutrients to every part of the brain. Without this flow, neurons would die quickly. In fact, brain tissue begins to suffer damage within minutes if oxygen is cut off. That's why strokes and cardiac arrests pose such a threat to brain health. The pink hue comes from oxygenated blood and the density of vessels in the tissue. Brain slices viewed during surgery or research often appear more pink or beige than the gray suggested by the name. In a preserved or dissected brain, the lack of blood flow makes the tissue duller, turning gray and white areas more clearly visible. Some brain regions also appear darker or lighter, depending on how much myelin they contain. Areas with dense myelination look whiter. Areas with fewer axons and more cell bodies appear grayer. Brain imaging tools like MRI can show these differences. In MRI scans, gray and white matter show up as different shades. This helps doctors and researchers see how structures change over time, how diseases progress, or how injuries affect brain networks. Understanding brain color and structure isn't just academic. It helps explain how the brain works in daily life. When a person learns a new skill, like playing the piano, both gray and white matter adapt. Neurons in motor and auditory areas fire more often. Their connections grow stronger. White matter pathways between these areas become more efficient. These changes don't happen all at once, and they don't follow just one path, but they depend on both kinds of tissue working in sync. When someone experiences a concussion, the damage often affects white matter. The axons may stretch or tear, disrupting signals. This kind of injury may not show up on basic imaging, but can still cause symptoms like fogginess or slowed thinking. Over time, the brain may repair or reroute connections, showing how plastic the system is. In Alzheimer's disease, gray matter shrinks as neurons die. This leads to memory loss, confusion, and eventually a breakdown in basic functions. But white matter also changes in Alzheimer's. The loss of connections contributes to the decline. Brain scans that measure both kinds of matter can give early warnings or track the disease's course. Some mental health conditions also show patterns in gray or white matter. People with schizophrenia may have reduced gray matter volume in areas tied to thinking and emotion. Those with depression may show changes in white matter pathways involved in mood regulation. These patterns don't tell the full story, but they help researchers understand what might be happening in the brain and guide new treatments. Even normal aging changes brain color and structure. Gray matter tends to shrink gradually over time. White matter may thin or show tiny lesions, especially in people with high blood pressure or diabetes. These changes don't always lead to problems, but they can affect memory, speed, and focus. Staying active physically, mentally, and socially can help maintain both gray and white matter into old age. So while it's easy to call the brain gray, that label leaves out much of what makes the brain work. The brain is a mix of cell bodies, axons, myelin, and blood vessels. It changes with use, age, and experience. Gray and white matter each have a role, and their interaction allows thought, movement, emotion, and awareness. The colors reflect structure, and the structure supports everything we do, from the simplest reflex to the most complex idea. Most people have felt it. You take a big bite of ice cream or a sip of a frozen drink, and suddenly a sharp pain shoots into your head. It feels like it's coming from deep inside your skull, like your brain itself is freezing. That's why it's called a brain freeze. But this name is misleading. The pain doesn't actually come from the brain. It's referred pain, caused by rapid cooling of the upper palate in the mouth. The brain has no pain receptors, so it can't feel cold or pain directly. The sensation we call brain freeze is the result of a nerve reaction in the mouth and head. The medical term for brain freeze is sphenopalatine ganglioneuralgia. That's a long name, but it simply refers to nerve pain involving the sphenopalatine ganglion, a group of nerves located behind the nose and upper mouth. These nerves help control blood flow and sensation in parts of the face and head. When something cold hits the roof of your mouth too fast, it triggers a sudden change in blood flow. Blood vessels in that area quickly constrict or narrow due to the cold. As soon as the mouth warms back up, they dilate or widen just as fast. This quick change creates pressure and stimulates nearby pain-sensitive nerves, especially branches of the trigeminal nerve. The trigeminal nerve is a major nerve that carries sensory information from the face to the brain. It has 3 main branches. One goes to the forehead, one to the cheek, and one to the jaw. The nerve also has smaller branches that serve the roof of the mouth and the upper sinuses. When those branches sense rapid cooling, they send a distress signal to the brain, but the brain can't always tell exactly where that signal is coming from. The result is referred pain, pain that's felt in a different place than where it started. In the case of a brain freeze, the pain feels like it's in the forehead or behind the eyes, even though the source is the mouth. Referred pain is not unique to brain freezes. It happens in other parts of the body too. A classic example is a heart attack. People having a heart attack often feel pain in their left arm or jaw, even though the problem is in the heart. This is because nerves from different parts of the body share common pathways to the brain. When the brain receives a strong signal from one of these shared pathways, it may misinterpret the source. The same thing happens with brain freeze. The brain reads the signal from the trigeminal nerve and thinks the pain is coming from the head or forehead. Not everyone gets brain freezes, and some people get them more often than others. This may be due to differences in nerve sensitivity, mouth anatomy, or how fast someone eats or drinks. People with migraines tend to be more sensitive to brain freezes. The trigeminal nerve plays a role in both conditions, so it makes sense that people prone to migraines might feel stronger or more frequent reactions when they eat or drink something cold. Brain freezes are usually harmless and last only a few seconds to a minute. The pain tends to peak quickly and then fade just as fast. Still, it can be intense and surprising. The key factor is how quickly the cold touches the palate. Sipping a cold drink slowly or letting ice cream melt slightly before eating it can reduce the chances of triggering a brain freeze. Once it starts, warming the roof of the mouth can help stop it. Pressing your tongue or thumb against the palate can transfer heat and reverse the blood vessel changes that caused the pain. Drinking warm water or breathing through your nose can also help warm the area more quickly. While brain freezes are brief, they show how sensitive and complex the nervous system is. The same nerve that helps you chew and feel your face also reacts to cold in the mouth and sends pain signals to the brain. This connection reminds us that the body is full of overlapping systems. Pain isn't just about injury. It's also about signals, timing, and how the brain interprets input. In rare cases, brain freeze-like pain might be confused with more serious conditions, especially if it happens without cold food or if it lasts longer than expected. People with frequent headaches, migraines, or sinus problems might feel similar sensations, but typical brain freezes follow a clear pattern. They happen soon after eating or drinking something cold, and they go away quickly. They don't require medical treatment and don't cause lasting harm. Brain imaging studies have looked at what happens during a brain freeze. Researchers have found that the anterior cerebral artery, which supplies blood to parts of the brain, temporarily narrows and then widens during the episode. This change in blood flow may also help trigger the pain. These findings are similar to what happens in some types of headaches, including migraines. That doesn't mean a brain freeze is a migraine, but it shows that some mechanisms may overlap. Understanding brain freeze helps explain how the body processes pain. It also shows how nerves respond to changes in temperature and blood flow. Even though the brain itself doesn't feel pain, It's involved in processing and interpreting pain signals from the rest of the body. When those signals are fast, strong, or confusing, the brain may place them in the wrong spot. That's how a cold mouth can create the illusion of a frozen brain. This misinterpretation doesn't cause harm, but it highlights how pain isn't just a physical response. It's also a perceptual one. The nervous system is efficient, but not perfect. It works fast to protect you, even if that means sounding a false alarm sometimes. Brain freeze is one of those false alarms. Brief, unpleasant, and a reminder that your body reacts to keep you safe. People who want to avoid brain freeze can take simple steps. Slow down when eating or drinking cold things. Let frozen items warm up slightly before putting them in your mouth. Keep cold foods from hitting the roof of your mouth directly. If you do get a brain freeze, press your tongue against the palate or sip warm water to speed recovery. These small changes can prevent that sudden jolt of pain that seems to come out of nowhere. In the end, brain freeze is more about the mouth and the nerves than the brain itself. The term makes it sound like your brain is under attack, but the real source is a group of nerves in your face reacting to cold. The pain is real, but the location is a trick. It's another example of how the body protects itself, even when the signals get crossed. The brain doesn't freeze. It just tries to make sense of the message, even if the result is a brief moment of confusion and discomfort. Many people believe they have a dominant learning style. Some say they are visual learners who absorb information best through images or diagrams. Others identify as auditory learners who prefer lectures or spoken instruction. Some claim to be kinesthetic learners who need to move or engage physically with material. This idea is popular in schools, training programs, and even corporate workshops. It feels intuitive. People do have preferences, but research does not support the idea that matching teaching methods to a preferred learning style improves learning outcomes. The evidence shows that this belief oversimplifies how people learn. The learning styles theory suggests that people can be sorted into fixed categories based on how they best take in information. The most common types are visual, auditory, reading, writing, and kinesthetic, sometimes called the VARK model. Advocates of the theory argue that if teachers tailor instruction to match a student's style, learning will be more effective. A visual learner should see charts, an auditory learner should hear explanations, and so on. But controlled studies have repeatedly failed to show that this approach leads to better performance. Researchers have tested the learning styles hypothesis in many ways. A typical test involves dividing students into groups based on their stated learning style. Each group receives the same material, but presented in different formats: visual, verbal, physical. If the theory were correct, students should perform better when taught in their preferred style. But in study after study, researchers have found no significant advantage. Students often do equally well or poorly, regardless of whether the instruction matches their supposed style. One reason the theory fails is that learning is not that simple. The brain processes information through multiple channels at once. Reading a diagram involves visual input, but also language. Listening to a story activates auditory regions and areas linked to memory and emotion. Solving a math problem may involve seeing numbers, hearing a process, and moving a pencil. Most tasks require a mix of inputs. The idea that one channel dominates ignores how the brain integrates information. Preference is not the same as effectiveness. A student may say they prefer watching videos, but that doesn't mean it's the best way for them to learn a topic. Preference can be shaped by habit, comfort, or what feels easy. Effective learning often involves challenge. Struggling with a concept, rephrasing it, and applying it in different ways helps memory. Feeling good about a method doesn't always mean it leads to lasting understanding. People also overestimate how well they learn when using their preferred style. This is called the illusion of learning. For example, someone may feel like they've mastered a topic after watching a video, but test results later show gaps in understanding. The content may have been easy to watch, but it didn't stick. In contrast, methods that feel harder, like writing summaries or practicing retrieval, often lead to better retention. The discomfort signals deeper processing. Cognitive science points to other factors that matter more than style. Prior knowledge, attention, practice, feedback, and motivation all play key roles in learning. Techniques like spaced repetition, retrieval practice, and elaboration are supported by decades of research. These methods work across subjects and learners. They focus on how memory works, rather than trying to fit instruction to a fixed category. Learning styles theory also runs into problems when applied broadly. Some subjects are naturally more visual, like geometry or art. Others rely more on text or sound, like literature or music. Trying to force every topic into a student's preferred format may not make sense. A kinesthetic approach might help in sports training, but may not be useful in abstract reasoning. Flexibility matters more than rigid style matching. In classrooms, the learning styles idea can create extra work for teachers without real benefits. It encourages dividing students into types and planning separate lessons, even though no evidence shows this helps. It can also lead to labeling. A student told they are a visual learner might avoid reading or writing, thinking those methods don't suit them. This can limit growth and confidence. Instead of matching style, research supports using multiple methods. Presenting information in more than one format, like combining images, text, and discussion, can enhance understanding. This is called dual coding. It works not because it matches a learning style, but because it engages the brain in different ways. When students hear an explanation and see a related image, they build stronger mental connections. This approach helps all learners, not just those who prefer visuals. Some people argue that learning styles theory boosts self-awareness. It gives learners a way to talk about how they like to study. That may be true, but it's not the same as evidence. Self-reflection can help students develop study habits, but it should be grounded in what works. Encouraging students to try different strategies and reflect on their outcomes builds useful skills. Sticking to a narrow style does not. Learning styles also don't explain differences in achievement. If they did, matching teaching to styles would close gaps. But there's no sign that tailoring instruction this way improves equity or helps struggling students catch up. Strong teaching practices, like clear explanations, active engagement, and timely feedback, benefit everyone. They matter more than style. Despite the lack of evidence, learning styles theory remains popular. It sounds scientific. It offers a quick answer to why some students succeed and others don't. It promises a fix, just match the style. But education is complex. Understanding takes time, practice, and support. No single trick replaces that process. The continued belief in learning styles may come from how it feels. When someone says they're a visual learner, they may be describing a pattern that works for them in some cases. They may enjoy diagrams or find reading easier than listening. That's useful to know, but it's not the same as a fixed style. Preferences can guide choices, but they should not limit opportunities. A better approach is to build a toolkit. Students can try visual aids, group discussion, written notes, teaching others, or hands-on practice. They can test what helps them remember and understand. They can use effective strategies even if they don't enjoy them at first. Over time, they learn how to learn, not just what to learn. Teachers can support this by offering varied instruction, not based on styles, but based on what supports understanding. This might mean using a diagram to show a process, a story to explain a concept, and a practice task to apply it. It means guiding students to think actively and giving them feedback on what works. It means building curiosity and confidence, not dividing learners into types. The brain is adaptable. It learns through patterns, practice, and meaning. No single pathway defines a learner. Instead of fitting students into boxes, education works best when it opens doors. Learning styles may feel right, but research shows that learning is more about engagement, effort, and feedback than about matching instruction to a label. Many parents believe that giving sugar to children causes hyperactivity. They see a child eat cake or candy and then run around, talk loudly, or act restless. It seems like the sugar is to blame. This idea is repeated in homes, schools, and media. It feels true because the timing lines up. A child eats sugar, then acts wild. But when researchers test this belief in controlled settings, the results don't support it. Sugar does not make children hyperactive. Controlled studies show no consistent link between sugar intake and behavior changes in children. This belief likely started in the 1970s, when a doctor named Benjamin Feingold suggested that food additives, including sugar, might cause hyperactivity in children. His diet plan excluded artificial colors, flavors, and some preservatives. Though it gained attention, follow-up research found weak evidence. Still, the idea that sugar affects behavior caught on. Over time, it became common knowledge, but common knowledge isn't always correct. Researchers have tested this claim many times. In a typical study, they take two groups of children and give one group sugar and the other a placebo, something that tastes sweet but contains no sugar, like a drink made with an artificial sweetener. The children, parents, and observers don't know who received which. This method avoids bias and isolates the effect of sugar alone. Across many studies, researchers found no meaningful difference in behavior between the two groups. Children who consumed sugar did not move more, talk more, or score higher on measures of activity or attention. One well-known study looked at children whose parents claimed they were sensitive to sugar. The parents believed sugar made their children more active, but when researchers tested this in a blind trial, even those children showed no behavioral change after consuming sugar. Interestingly, when parents were told their child had consumed sugar, even when they hadn't, the parents rated the child as more hyperactive. This points to expectation, not biology. The belief in the sugar hyperactivity link may come from how people notice and remember events. If a child eats sugar at a birthday party and then acts excited, parents may connect the two. But birthday parties are full of activity, noise, and social energy. Children run around because the setting is exciting, not because of the cake. If the same child ate sugar alone in a quiet room, their behavior might not change. But we tend to remember events that confirm our beliefs and forget the ones that don't. This is called confirmation bias. There's also a social factor. When children expect to feel energetic after sugar, they may act that way. They learn from adults and from experience. If parents or teachers joke that sugar makes kids go crazy, children may respond with more energy. This doesn't mean they're misbehaving on purpose. It shows how beliefs and setting shape behavior. Some people argue that sugar may affect certain children more than others. For example, they suggest that children with ADHD might be more sensitive to sugar. But studies have not found a consistent link there either. Sugar does not worsen symptoms of attention deficit hyperactivity disorder. ADHD is a complex condition that involves genetics, brain chemistry, and environment. Diet may play a role, but sugar alone does not cause or trigger it. That said, sugar does affect the body in other ways. When you eat sugar, blood glucose levels rise. This gives the body quick energy. In response, the pancreas releases insulin, which helps move sugar into cells. This process is normal. But if someone eats large amounts of sugar without other nutrients, the glucose spike may be followed by a drop. Some people believe this drop causes fatigue or mood swings, but research shows that in children, these changes are mild and not linked to hyperactivity. Too much sugar also affects long-term health. Diets high in added sugar can lead to weight gain, tooth decay, and increased risk of diabetes and heart disease. These concerns are real and backed by strong evidence, but they are separate from behavior in the short term. Saying sugar causes hyperactivity distracts from the real effects it can have on the body over time. It's also worth looking at what kind of sugar is being discussed. Not all sugars are the same. Natural sugars in fruit come with fiber, water, and nutrients. These slow digestion and reduce blood sugar spikes. Added sugars in candy, soda, and baked goods often come with little nutritional value. These added sugars are the ones most linked to health risks. But again, even added sugar does not lead to hyperactivity in controlled studies. Beverages are another area where confusion happens. Sugary drinks often contain caffeine, which is a stimulant. If a child drinks a soda and then becomes more active, caffeine, not sugar, may be the cause. Caffeine affects the central nervous system and can make children more alert or restless, especially in high doses. This adds another layer of confusion to the sugar story. People may blame sugar for effects actually caused by another ingredient. In some cases, sugar is one part of a larger pattern. A child may eat sweets at a time when they are already tired, overstimulated, or hungry. These conditions can affect mood and behavior. If a child skips meals and then eats a sugary snack, they may get a short burst of energy, followed by a crash. But again, this isn't hyperactivity in the clinical sense. It's a shift in energy linked to eating patterns, not a direct behavioral effect of sugar. The sugar hyperactivity myth has stuck around because it's simple and easy to explain. Parents want answers for why their child might be acting out. Sugar provides an obvious target, but behavior in children is shaped by many factors: sleep, stress, attention, activity level, environment, and more. Blaming sugar may offer a quick explanation, but it doesn't solve the real issues. What does help is routine, sleep, balanced meals, and chances for active play. These support focus and mood far more than cutting out sugar. That doesn't mean sugar should be unlimited, but moderation is more useful than strict bans. Demonizing sugar can also backfire. It may lead to power struggles, food guilt, or binge behavior. Teaching children how to enjoy sweets as part of a balanced diet is a healthier, long-term strategy. In classrooms, teachers may notice bursts of energy after lunch or snack time and assume sugar is to blame. But movement, peer interaction, and noise levels can all spike after a break. If every increase in energy is pinned on sugar, the true causes may be missed. Understanding the setting helps separate correlation from causation. Many nutrition myths last because they give a simple answer to a complex question. The sugar and hyperactivity link is one of the most enduring, even though it doesn't hold up under careful study. Children are active, curious, and energetic by nature. Sometimes they get loud or restless. That's not always a problem to fix. It's part of normal development. Sugar doesn't turn calm children into wild ones. What shapes behavior is more often the environment, expectations, and routine, not the frosting on the cupcake. The idea that listening to classical music makes babies smarter became popular in the 1990s. Many parents started playing Mozart to their newborns, hoping to give them a head start in life. Toy companies and music producers quickly responded by creating products aimed at boosting infant intelligence through music. This became known as the Mozart Effect. The idea was simple and appealing. Play classical music, and your baby will become more intelligent. But when researchers looked more closely at the evidence, they found that the claim does not hold up. Listening to classical music does not cause lasting improvements in a baby's intelligence or cognitive abilities. The original study behind the Mozart Effect didn't even involve babies. It was published in 1993 by researchers at the University of California, Irvine. The study looked at college students, not infants. The students listened to 10 minutes of a Mozart sonata before taking a spatial reasoning test. On average, the students who heard Mozart scored slightly higher than those who sat in silence or listened to relaxation instructions. The effect lasted about 10 to 15 minutes. It was small, short-lived, and limited to one type of thinking, mental rotation of shapes. Despite these modest findings, the media picked up the story and turned it into a much larger claim. Headlines suggested that Mozart could raise IQ, and the idea quickly spread. Soon, people began to believe that listening to classical music could make babies smarter, more creative, or better at math. Some states even began distributing classical music CDs to new parents. The message was clear: playing Mozart was a smart parenting move. But later studies tried to repeat the results and often found no effect or only minor, temporary changes. When researchers tested children or infants, they found no consistent benefit from listening to classical music. Cognitive development in babies depends on many factors: genetics, health, nutrition, attention, and interaction, not short bursts of passive listening. Babies' brains do grow quickly, and they respond to sound from birth. Even in the womb, they can hear muffled voices and music. After birth, they react to tone, pitch, and rhythm. They may calm down when hearing soft music or become more alert with fast beats. Music can soothe or stimulate, but this response doesn't mean it makes them smarter. It means their auditory system is working, and they are engaging with sound in a natural way. There's also no evidence that Mozart in particular has a unique effect on intelligence. The choice of Mozart in the original study was likely arbitrary. Any enjoyable or engaging music might have produced a similar short-term response. Later experiments tried using other types of music: pop, jazz, or even silence. Sometimes, simply enjoying the experience led to better focus or alertness for a few minutes. It wasn't about the music making people smarter. It was about being in a good mood or having heightened attention for a short time. Mood and arousal do affect performance. If someone feels alert and calm, they may do better on a test. Music can help create that state, but this is not the same as improving intelligence. Intelligence involves reasoning, memory, learning, and problem solving. These skills build over time through active experience and practice, not by listening passively. What helps babies develop cognitive skills is interaction with people and the world around them. Talking, reading, singing, and playing with a baby supports brain development. These activities build language, memory, motor skills, and emotional understanding. When a caregiver sings to a baby or rocks them to a lullaby, the baby is not just hearing sound. They are bonding, making eye contact, and learning patterns of communication. This kind of engagement promotes brain growth far more than background music played from a speaker. Touch, movement, and shared attention also matter. When babies reach for toys, crawl around the room, or explore new textures, they are building neural connections. When adults respond to a baby's actions, smiling, speaking, or copying sounds, the baby learns cause and effect. These moments support development in ways that music alone cannot. Some parents worry that if they don't play Mozart or use special learning tools, their baby will fall behind. But the best support for early brain development is simple, consistent, and human. Loving interaction, play, good nutrition, and enough sleep do far more than any audio program. That doesn't mean music has no place in a baby's life. Music can be fun, calming, or energizing. Singing to a baby helps with language and bonding. Dancing with a baby encourages motor coordination and rhythm. Musical games like clapping or finger plays build timing and memory. These are active, shared experiences, not passive listening in the background. Music education later in life can also support learning. Children who take music lessons often show improved attention, memory, and coordination. But these benefits come from active practice and training, not from listening alone. Learning to play an instrument challenges the brain in ways that build cognitive skills. It takes effort, repetition, and problem solving. Claims that music makes babies smarter often come from marketing rather than science. Products that promise to boost intelligence through sound tap into parental hopes and fears. But well-controlled research does not support those claims. Intelligence develops through rich experiences, not magic inputs. Parents may still enjoy playing classical music at home. There's nothing wrong with that. If a parent enjoys Mozart, the baby may enjoy it too. A calm home environment, filled with music, conversation, and care, supports development. But the key is not the music itself, it's the connection it helps create. Some researchers have noted that labeling a baby as smarter based on passive listening sends the wrong message. It turns learning into a product instead of a process. Babies are not containers to fill with information. They are active learners, curious from the start. They need space to explore, faces to watch, voices to hear, and hands to hold. These are the tools that shape a growing brain. In summary, listening to classical music does not make babies smarter. There is no evidence for long-term cognitive improvement from music exposure alone. The original Mozart Effect was short-lived and seen in adults, not infants. Music can affect mood and attention in the moment, but it does not raise IQ. Real development comes from interaction, play, movement, and care. Music may support that process, but it is not a shortcut to intelligence. The idea that cognitive decline begins at age 30 shows up in articles, memory ads, and casual conversations. People in their early 30s may hear they've hit a turning point, that their minds are already past their peak. This message can feel discouraging, but it oversimplifies how the brain changes with age. While some mental abilities begin to slow in early adulthood, others remain stable or even improve for decades. Aging affects the brain in many ways, but it does not mean a steady drop in thinking ability from 30 onward. Cognition is not one thing. It includes several types of thinking skills. Processing speed, working memory, long-term memory, vocabulary, reasoning, spatial skills, and attention all develop along different paths. It's true that processing speed begins to slow in early adulthood. This means that it may take a little longer to react, switch tasks, or solve a problem that requires speed. But the decline is usually gradual and often goes unnoticed in daily life. Working memory, the ability to hold and manipulate information in the mind, can also start to show small declines in early adulthood. For example, remembering a phone number long enough to dial it or doing mental math may feel slightly more effortful. But again, the changes are subtle and do not prevent people from functioning well. In many cases, people find ways to adapt. They write things down, use reminders, or rely on routines to support memory and attention. Other abilities hold steady or improve. Vocabulary, for example, tends to grow with age. This includes both the number of words a person knows and the ability to use them well. Adults in their 40s, 50s, and even 60s often perform better on vocabulary tests than younger adults. This is because vocabulary is part of crystallized intelligence, knowledge built through experience. Reading, conversation, work, and learning continue to build this storehouse of information over time. General knowledge also grows with age. Older adults tend to score higher on tests that ask about facts, history, and concepts. This kind of intelligence doesn't rely on fast thinking, but on accumulated understanding. In real-world situations, this often matters more than quick recall. For example, solving a complex problem at work or giving advice to someone may benefit more from experience and insight than from rapid calculations. Reasoning skills show a mixed pattern. Fluid reasoning, the ability to solve new problems without relying on past knowledge, may peak in early adulthood and decline slowly after that. But many tasks blend fluid and crystallized reasoning. When older adults draw on their background and connect it to new information, they often perform just as well or better than younger adults. In fact, some studies show that older workers can outperform younger ones in roles that require judgment, emotional control, or planning. Emotional regulation tends to improve with age. Many older adults report greater satisfaction, better control over emotions, and less reactivity. This may support clearer thinking under stress. Experience teaches people how to handle uncertainty, solve conflicts, and let go of unimportant worries. These changes may not show up on standard cognitive tests, but they affect how people approach problems and relationships. In some cases, what looks like cognitive decline is actually a shift in priorities. Younger adults may perform better on lab-based tasks that require speed or novelty. Older adults may prefer accuracy, reflection, or meaningful content. If a test rewards quick answers, younger participants may seem to have an edge. But in complex, open-ended tasks, older adults may bring better strategy and focus. Brain imaging studies show structural changes with age. The volume of certain brain areas, such as the prefrontal cortex and hippocampus, may shrink over time. White matter, the insulation that helps signals travel between regions, also shows wear. These changes may affect memory, attention, and processing, but the brain also adapts. Older adults often show more balanced activity across both hemispheres, suggesting that the brain recruits extra resources to complete tasks. This compensation helps maintain performance even as some structures change. Neuroplasticity continues into old age. The brain remains capable of forming new connections, learning skills, and adapting to challenges. Exercise, learning, social engagement, and sleep all support cognitive health. People who stay mentally and physically active tend to perform better on memory and attention tasks than those who are inactive. This shows that lifestyle matters as much as age. One example is the concept of cognitive reserve. This refers to the brain's ability to cope with damage or decline by using alternative strategies. People with higher education, complex work experience, or lifelong learning habits tend to have more cognitive reserve. They may show fewer signs of decline or delay the onset of symptoms, even when physical changes are present in the brain. Not all age-related changes are due to aging alone. Stress, sleep problems, depression, medication side effects, and chronic illness can all affect thinking. These issues can appear at any age, but may become more common in midlife or later. Addressing them can improve cognitive function. For example, treating sleep apnea or managing high blood pressure may improve memory and concentration. There are also myths about memory loss in aging. Forgetting names, misplacing items, or taking longer to learn new technology are common and usually not signs of serious decline. These changes reflect slower retrieval, not lost knowledge. The information is still there. It just takes longer to access. Older adults may need more repetition or time to learn something new. But once learned, the knowledge often stays stable. In contrast, true cognitive decline, such as dementia, is not a normal part of aging. Dementia involves significant loss of memory, judgment, and function that interferes with daily life. It is caused by disease, not age itself. While risk increases with age, most people do not develop dementia. Distinguishing between normal aging and disease is important, and early signs should be evaluated by a doctor. Cognitive assessments often show a complex picture. One person may do well on language, but score lower on memory. Another may struggle with multitasking, but have excellent reasoning. No single test captures the full range of thinking. Context, background, and daily function all matter. A lower score on a lab task may not mean much if the person is managing work, relationships, and hobbies well. People in their 30s may notice small changes in focus or recall. This doesn't mean they are in decline. It may reflect changing demands, stress, or shifts in sleep and attention. In fact, many people report feeling more capable in their 30s than in their 20s. They have more confidence, knowledge, and stability. Their brains may be slower in some ways, but sharper in others. Focusing only on decline gives the wrong message. It makes people anxious and may discourage learning or growth. Instead, it's more accurate to say that the brain changes with age. Some functions may slow, others grow. The goal is not to avoid all change, but to support health and learning throughout life. A person at 30 is not in mental decline. They are still building, adapting, and growing in ways that matter. The idea that you can learn complex material while you sleep has been around for decades. It shows up in books, movies, and ads for language tapes or self-help programs. The promise sounds appealing. Play an audio recording while you sleep and wake up knowing a new language, a list of facts, or a set of skills. But this idea is false. Complex learning, like grammar, vocabulary, or detailed knowledge, doesn't happen during sleep. The brain doesn't absorb new, structured content while you are unconscious. What the brain does do is consolidate learning that already took place while you were awake. During sleep, the brain is active. It doesn't shut down, but it works differently than when you're awake. Sleep includes several stages, including light sleep, deep sleep, and REM, rapid eye movement sleep. Each stage plays a role in memory, restoration, and brain maintenance. Some studies show that during certain sleep stages, especially deep sleep and REM sleep, the brain replays parts of the day's experiences. This is how it strengthens memories and organizes what you've learned. But this process depends on input from the waking state. It's not a time when the brain takes in brand new information from the outside world. Researchers have tested the idea of sleep learning using audio recordings. In these studies, participants wear headphones during sleep while researchers play sounds, words, or phrases. In some cases, simple associations or word pairs played during light sleep may lead to a slight effect. For example, if someone learns to associate a smell with a word during the day and hears that word again during sleep, they may recall it a little better. But these effects are small and limited to very basic information. Complex tasks like learning a new language, understanding math, or mastering a concept do not improve just by listening during sleep. One key reason is that the brain blocks most sensory input during sleep. It's a built-in defense that protects the brain's rest time. If external sounds reach the brain in the same way they do while awake, every noise in the environment would disrupt sleep. Instead, the brain uses sleep time to reset certain systems and repair others. It processes what has already been learned, but is not in a state to take in structured information from scratch. Sleep is essential for learning, but not in the way sleep learning products suggest. When you study something new, your brain forms fragile memory traces. These traces need to be stabilized and strengthened so you can recall them later. Sleep plays a major role in this stabilization process. During deep sleep, neurons in the hippocampus replay patterns from earlier in the day. These patterns help move memories from short-term to long-term storage, often transferring them to areas in the neocortex. This process is called memory consolidation. It doesn't add new material, it improves access to what was already there. Sleep also improves problem-solving and insight. After sleeping, people sometimes find that a problem seems easier, or that they remember something they couldn't recall the day before. This isn't because they learned the solution during sleep. It's because sleep allows the brain to reorganize and make connections. This is one reason why cramming all night before a test is less effective than reviewing material and getting a full night of sleep. Sleep strengthens the learning that occurred while awake. Without sleep, memory is weaker and less accurate. Some advertisers claim that listening to motivational audio, affirmations, or language lessons during sleep will sink into the subconscious. They imply that sleep is an open door to hidden learning. But the brain doesn't process audio in that way while asleep. Hearing a word repeatedly doesn't lead to understanding it. Learning involves attention, context, repetition, and feedback, none of which happen when you're unconscious. To truly learn something, the brain needs to work with the information actively. That means noticing patterns, making mistakes, and connecting ideas. These steps require wakeful focus. Repetition alone is not enough. Even during the day, listening passively to material without engagement has limited effect. Listening while asleep removes even the chance for engagement. That said, there are ways sleep can support learning. Reviewing material just before sleep may help strengthen it during the night. If you study vocabulary words or practice a skill and then go to bed, your brain is more likely to replay and store that material. This is not the same as learning while asleep. It's using sleep to lock in daytime learning. Timing matters, and rest enhances memory, but it does not substitute for active practice. People who try to learn while asleep may find themselves frustrated. They might wake up without remembering any of what was played. This isn't a sign of failure. It's a sign that the brain is doing what it's supposed to do, ignoring outside input so it can process internal information. Forcing learning during sleep doesn't improve results and may even interfere with rest. Audio during sleep can disrupt sleep cycles, especially if the volume changes or the material becomes emotionally charged. There's also a difference between hearing and listening. The brain may register a sound during sleep, but that's not the same as understanding it. For example, a loud noise may cause a sleeper to turn or wake up, but they won't remember what the sound was. If words or music play during sleep, the sleeper may have vague dreams or sensations related to the sounds, but they won't absorb structured lessons from them. Dreams don't help with learning in a direct way either. While dreams may include fragments of daily life, they are more about processing emotions and random memories than solving problems or learning new facts. Some people feel creative after dreaming, and dreams may inspire ideas, but they don't replace practice, reading, or repetition. Creativity may get a boost, but content does not appear fully formed after sleep. The interest in sleep learning may come from a desire to save time. People want to be more productive, use every hour, and find shortcuts. Sleep seems like wasted time in a culture that values constant activity, but the science shows the opposite. Sleep is productive. It plays a role in healing, memory, emotional regulation, and attention. Using it wisely means protecting it, not trying to fill it with more tasks. If you want to learn something new, focus on what happens while awake. Use strategies that match how memory works: spaced repetition, testing yourself, summarizing, and applying the material in different contexts. Then get enough sleep. That combination works better than any attempt to multitask through the night. The myth of sleep learning continues because it's easy to believe and hard to disprove in everyday life. People may feel like something's stuck after hearing it in their sleep, but that's more likely due to previous exposure or coincidence. Research does not support the claim that structured learning occurs during sleep. The brain uses that time to reinforce what it already encountered, not to learn new lessons from scratch.